Okay, let's make a nice early start because some of the things will take a while to go through tonight. So there will be a few more people obviously coming as we go, but let's begin anyway. Welcome to the February meeting of the Mornington Peninsula Astronomical Society, and good to see everyone here, those that are brave coming out in person. Now, as you see on this leading slide here, some of the things that have happened in the last month or so. If you look at the top left-hand side, we see the Starlink satellites that came to grief from a launch around the 3rd of February. 49 were actually launched and 40 came down because of an outburst from the sun, which does occur occasionally. And what they do is they heat up the atmosphere, cause it to expand a bit, which of course increases the drag. And in the case of the Starlinks, they don't go up to low Earth orbit straight away. They only go up about 200 kilometres. They're tested and then they're boosted up higher once they all pass the test. So they got the halfway mark, and unfortunately for them, the density of the atmosphere increased at that level significantly, and so those 40 came down, or are in the process of coming down, those that haven't already. But a lot of astrophotographers around the world are not going to be too fussed about that, I imagine. But 40 being lost is nothing compared to the thousands that are up there already, and many thousands yet to come. More exciting is the image on the left, which is the first image taken of a star by the James Webb Space Telescope, which is now out at the L2 Lagrange point. And you see 18 separate images there. If you went and bought a telescope from the shop and brought it home and that was your first image, you'd be somewhat worried. That was pointed at a single star, a magnitude 6.9 star, so easily visible in binoculars, even if slightly out of most people's naked eye vision. And as you see, you've got 18 images shown there, some of which were quite blurry. And that was considered to be a success, that they managed to get them all pointing roughly in the right direction. The mirror is shown at the bottom left-hand side, being the 18 hexagons. And each one of those hexagons is producing one image of the star, and they haven't yet aligned them properly. The image at the bottom left is actually a selfie that was taken by the James Webb Space Telescope out there at the L2 point. And as you see, one of the mirrors is lit up due to this magnitude 6.9 star in Ursa Major, so we can't see it in our night sky here in the southern hemisphere. But they're quietly confident, as we'll see in a moment. Over on the far right hand side is showing, going round and round and round and round, is the inner planets at the centre, followed by the outer circle, which is showing Jupiter, and ahead of Jupiter and behind Jupiter are these green blobs of the asteroids. This is actual based on NASA data, and those are the so-called Trojan asteroids. And that becomes relevant because one of the things that we will cover today is the Lagrange points, and those are two of the Lagrange points of Jupiter that you're actually seeing there. Now, by naming convention, the asteroids that are following Jupiter, the ones behind, are named after Trojan characters from the Greco-Trojan War, you know, the ones from the Trojan horse, the story of the Trojan horse, and the so-called Trojan asteroids that are leading it are given the Greek names from the Greek side. So one side of asteroids is named after the Greeks, and the other side is named after the Trojans. Bit of trivia there. Now this goes for 2 or 3 minutes, and this was released when the James Webb Telescope sent back its first images.
Well, first of all, the first evaluation images came in the middle of the night, but the team all came in, and we gathered and we evaluated whether the camera was working well enough for us to proceed on with the alignment. And as we analyzed those first, photons, if you will, the team was pretty positive that the camera was working properly and the instrument was working properly. So we picked a star that was very bright and didn't have any stars near it that would contaminate the image. We know that the primary mirror segments aren't aligned, so they actually act like 18 separate telescopes, and we expect to see 18 separate images, one for each mirror, that are a little bit blurry at this point because we haven't aligned or focused anything. And so we pointed at a bright star and we made a mosaic. We actually took the near-infrared camera and we took images in different parts of the sky, and then we looked for the 18 spots from the 18 different telescopes, if you will. And we were very excited to find them. And the 18 spots were actually fairly close to each other. So really everything was very close to what was predicted. We've identified which of the 18 spots is which mirror. At this point, we even know which ones are from the wings. And it turns out one of the wings, you can actually see those 3 spots are a little farther over. And that's sort of what we expected. So we've identified all 18 spots, and the next step is to make an array of them. And then we're ready to start what we call global alignment, which is when each of those 18 spots will start to be aligned and focused. And that's sort of the last step before we take those 18 spots and put them on top of each other to start forming a single star going through the 18 separate telescopes. That's the work that will be starting soon. We also took a selfie of the primary mirror. We took an image of the primary mirror, and that helps us understand the alignment of the telescope, especially the primary mirror, to the camera itself and the instruments. There's actually a special lens in the near-infrared camera that you can put in, and it allows you to take a picture of the primary mirror itself. And in this particular case, one of the segments is pointing at a star, so that is the segment that lights up. But you can see the outline through the shadows of all 18 segments, and you also can see the outline of what's inside of the instrument itself, and we can see how well that primary mirror in the telescope is aligned to the instrument. And that gives us some initial confidence that the alignment looks good, and that's a good starting point for doing the alignment of the telescope. We have now gotten some data looking through focus, and we've been able to see that we don't see any surprises in the shapes of the mirrors that we're looking at. So far so good, but we do have a long way to go.
Okay, so for tonight, welcome anyone who's a new member of the Society. I don't think there's any new members here that I can see, but if there are, please feel free to come up and say hello during the break at the end. I'll quickly go through the events past month and coming month of the Society. As I say, I'll just keep it very brief tonight. The main video tonight is actually all about the beginning of time by a theoretical astrophysicist from the Fermi National Laboratory in the USA, University of Chicago. Very good speaker. We'll follow that by Sky for the Month, which will be getting on for around about 20 past 9, I would think, by the time the video finishes. Then we'll break for the tea break. Those who wish to look through the telescopes and socialise outside after the tea break, feel free. Those who wish to come in and watch the videos explaining all about the Lagrange Points, which is one of the Lagrange Points, the L2 one, is where the James Webb Space Telescope is currently parked. This will explain all about the 5 Lagrange points, what they are, what's peculiar to them, what's actually sitting on them at the moment, and what's planned to be sitting on them in the future. Ranging from telescopes to colonies. So very, very interesting. Then we'll close at the end by something musical, but it's around about the tides and how the tides are generated on the Earth. This is produced by the Japanese space agency JAXA, and a very good explanation of how the tides are created on Earth visually. And down the bottom right there, the merchandise has already started with the James Webb Telescope. There's earrings on the left, and on the right there's a wall clock with a mirror background that you can buy. And the one in the middle, anyone guess what that is? Yes, it's a James Webb Telescope cookie cutter, and so you can actually bake your own James Webb Telescope mirrors. Right, recent events. We obviously had to call off our scheduled public nights in January due to the COVID restrictions. We had a members working bee barbecue that did go ahead on the 22nd of January. We had a committee meeting that looked at the cameras on site, and indeed a few more cameras have gone in since then. I think there's another 1 or 2 yet to go as well. We're looking at the grant that we have received now for the audio visuals, We looked at the sundial plans. This is the Ian Sullivan sundial shown at the bottom of the screen there. You probably noticed a very large rock on the way in that wasn't there last time you came, and that's where the sundial will eventually live. I think the rock weighs the best part of a tonne, I would think. One of the challenges will be mounting that solid brass sundial onto it. That sundial is one that has been customised to be accurate for here at the Briars as well, so not as if you could take it far away and use it, so it's even got analemic correction on it. Public night in February, we changed, instead of being the public, it was a members only night, and we had probably about 15-20 members there for that one, so that was pretty good to have that. Moving on to coming up, this Saturday we've got the Telescope Learning Day. In past years that's been an annual event. This year there'll be 2. We planned to have 2 last year, but unfortunately COVID restrictions killed the second one. So the first one is this Saturday, starting about 4 o'clock. There'll be a bit of a sausage sizzle type barbecue with it. And effectively, if you want to learn anything about telescopes, or you have a telescope in bits and you're interested in putting it together or finding out what pieces are missing, bring it along, and our members will show you that evening. Now, you don't need to book, you just need to turn up and QR code yourself in and wear a mask indoors, that sort of thing, unless you've got an exemption. Next committee meeting will be a week from now, and our first public stargazing night with the conditions easing will be on the 4th of March, which is always the first Friday of the month. And we're yet to figure out the speaker for that, because we lost one of the speakers who was due to speak then. He's out of action for a little while, unfortunately, so we'll be looking for another to fill that spot. Next meeting here will be on the 16th of March, and then further afield after the next meeting we've got the musical stargazing night and trivia and prizes where they give away a telescope as part of it as well. And that will be on Saturday the 26th of March. Bookings for that are online. If you haven't checked your emails through Scorpius, the details were posted there some days ago about how to go about booking for that one. And that's a collaboration with the Cranbourne Lions concert band. So this is a different band to the one that we did the collaboration with a couple of years ago here. So it will be a very different thing from the concert that was actually done at that time, but it will involve live music from them as well. We've got our first confirmed school night since reopening up. It will be the 30th of March out at Merrick's Lodge again, and that one is always very good. They're usually very keen girls from that visiting school down there at Merrick's. And in April, the Astronomical Society of Victoria this year is hosting the NASA, the National Australian Convention of Amateur Astronomers. This is a get-together once every 2 years of the astronomers across amateur astronomers primarily across Australia and sometimes from New Zealand, depending on the travel restrictions at the time. This year, due to so much COVID uncertainty and risk of cancellations with hotels involved, it won't be a face-to-face get-together. In this particular one, it will be an online event instead. Anyone is able to dial in for free and listen to the talks that are there, and maybe even ask a question if they make that facility available, which I'm pretty sure they will. That will begin at 9 o'clock on that Saturday, which is the Saturday of Easter, and then it will also carry on the following Saturday. So it will be an entirely online event, free to anyone, and we'll post the details of that with the link and everything when that becomes available. It will go out on email and on the members' Facebook page as well. So that's quite exciting. And the next one is probably going to be up at the Parkes Radio Telescope, because they missed out last time, unfortunately, due to the COVID lockdowns. So tonight's talk is all about the beginning of time and the universe since then, and what's going to happen before that time and what's going to happen after the universe. So a very interesting talk by Professor Dan Hooper from the University of Chicago. He certainly knows his stuff. It goes for about an hour, followed by about 20 minutes of questions afterwards. So we will go until probably about getting on for about 9:30. If you need to get up and stretch your legs or go out and have a cup of coffee, feel free to do so. Just do so quietly, and we'll leave this light on in the middle here, number one, so that where we're recording this, you can actually see me, and I'm not standing here in a complete shroud of darkness. And number two, it will enable you to get out safely if you need to go out for a bit of a break and then come back in.
Thanks. Thanks everyone for coming out. I want to start by saying it's really exciting to see such a packed room full of science enthusiasts. At least in my country, people are constantly lamenting the lack of the public's support or interest in science. And yet, when I come out to give talks like this, you all show up. So they're wrong. And thank you for helping me to prove them wrong tonight. So, when you think back across history, people of all times and all cultures have something in common. They all looked up at the night sky, and they all wondered about their universe and how it came to be. In this respect, we have a lot in common with our ancient ancestors. But in one way, we're very different indeed. We're different because we live at a very special time in history where, for the first time, when we look up at the night sky, we more or less understand what it is we're looking at. It's a privileged time in this sense. Take this image, for example. Okay. This is an image from the space telescope called Hubble. It's part of the program we know as the Hubble Deep Field. Most of the blotches you see in this image, these blotches of light, are pictures of galaxies, similar in size and shape to our own Milky Way. But because it takes time for light to travel across space, this image doesn't accurately depict what those galaxies are like today, but rather what they looked like more than 13 billion years ago, only a few 100 million years after the Big Bang. Our universe was a very different place then. It's much more compact and much hotter, filled with different kinds of things. And we more or less understand how and why it has evolved and changed in the ways it has to become the universe we live in. A little over 100 years ago, physicists didn't even have the foggiest idea how to ask these sorts of questions, much less how to answer them. We didn't know how our universe had changed or evolved or began. In fact, we didn't even know how to ask a question like, how could space change? We thought of space as an unchanging backdrop, something that objects could move through. But we didn't ever use verbs in connection with space. Space never did anything in Newtonian physics. But now, we think of space as something that can change and evolve, expand, contract, warp, curve. And we can thank that change, or give thanks for that change, to the ideas of Albert Einstein. So he was the one who taught us that space was more exciting than the static backdrop that Isaac Newton told us about. In 1915, with his general theory of relativity, he taught us that space can change, it can do things, it can be dynamic. And in fact, you can use these equations, the ones he published in 1915, to show that the space that makes up our universe can do a lot of things, but it can't stay the same. If you take those equations, you can picture a more or less uniform body of space filled with some amount of matter, you find invariably, without exception, that it has to either be expanding or contracting. And in 1929, the great astronomer Edwin Hubble observed for the first time that our universe is in fact expanding. Points in space are getting farther apart from each other as time progresses, causing the universe to steadily become colder and less dense and bigger than it was in the past. So, my guess is that everybody in this room has at some point heard that space is expanding, that our universe is expanding with time. But my other guess is that most of you don't really know what that means. you're probably picturing a situation where there's a bunch of stuff in space or a part of space, and it's slowly moving out of it, occupying a bigger volume. I want to remove that image from your brains. That is not what cosmologists mean when they say space is expanding. What Hubble actually saw through his telescope in the 1920s was that all the galaxies he could see were moving away from us. They were receding. And the farther away a given galaxy was, the faster he observed it to be moving away. Now, it's possible that that data would be consistent with an idea that we were like in the middle of some big cosmic explosion, everything's just moving away from us. But in fact, that's not the case. If you look at the universe as a whole, combine all the data we have, what you find is that if you were in a different galaxy and looked out at your neighboring galaxies, you would see the same thing Hubble did. Everything is moving away from every other point in space all the time. If you're like most people, you're probably asking yourself what I find to be a very predictable question around this time. It's predictable because I've given enough talks like this to know that that's probably what's going through 70 or 80% of your minds right now. And you're asking, what is space expanding into, right? Show me your hand if you were kind of wondering that. Yeah, okay, I told you. So it sounds like a reasonable question, but it doesn't have a good answer. It doesn't have a good answer because if space were expanding into something, what would we call that something? Space. All right, that's not what we mean. When I tell you that space is expanding, when a cosmologist says that space is expanding, what they mean is that all of space, not some of it, is expanding. The volume of any piece of space is bigger now than it was in the past and will be bigger still in the future. If you have a hard time picturing space expanding without something for it to expand into, I'll teach you a trick. This is something I came up with when I was a grad student and I was struggling with these ideas like I imagine a lot of you are right now. So the mental trick involves this. So I say I look at this room, I want to measure the size of this room. So what do? I find myself a meter stick. I run over there, I lay the meter stick down, one after the other, until I find out that this is 15 meters from side to side. Then I wait a little while, I do it again, make similar measurement, but this time I find it takes 16 meter stick lengths. How do I interpret this information? Well, I have two ways I could do it. I could say, I've just measured that the room is expanding, it's growing in time. Or, equally well, I could say, the meter stick is shrinking. Both are completely compatible with the data I've just described. But I could imagine objections. You could say, well, you can tell whether the meter stick is shrinking by comparing it. I can go over here and see, does this take 2 meter sticks or 2.5 or something? And does that change? Because if the meter stick is shrinking, then you could tell by comparing it to other things. So I say, okay, I'm going to refine my hypothesis, saying that everything in this room is together shrinking in unison. That will look just like the room expanding. So taking this back to cosmology, if you're uncomfortable with the idea of space expanding without expanding into something, you can conveniently instead think of everything in space, including the constants like the speed of light, are all shrinking together at the same time. So if space is expanding, which it is, and it has been for a long time, we can deduce that in the past, any given volume of space must have been smaller. And since it contains the same kinds of matter and stuff, it must have been denser in the past. And when you take a gas of particles, say, and compress it, it gets hotter. So Hubble's observation carried with it profound implications about our universe's past. This is at the heart of what we mean by the Big Bang Theory, the idea that over billions of years, our universe expanded and evolved from a hot, dense state into the universe that we see all around us today. Now, when you think about the Big Bang, or when it's usually described, you're probably tempted to picture something like a cosmic explosion. When somebody says the temperature a trillionth of a second after the Big Bang was something or other, or the density a minute after the Big Bang was whatever, or nuclear fusion was taking place a second after the Big Bang, you might think it happened somewhere in space. That's not what we mean. When I tell you that the Big Bang was at a certain temperature, or the universe was at a certain temperature just after the Big Bang, what I mean is all of space. That temperature was everywhere. Those densities were everywhere. Those extreme, mind-boggling conditions that the Big Bang describes were a state that persisted throughout all of space, everywhere in the universe. It's not an explosion, it's not an event, it's not a location, it's not an object. It's a state that our entire universe was in 13.8 billion years ago. All right, so let's take a step back and walk through a timeline of our universe's cosmic history. So on this scale, you see a couple of key events. You can start a couple of hundred million years after the Big Bang. That's when the first stars begin to form. Those stars were pretty different from the ones we see in our universe today. The first stars were much bigger and they were shorter lived. They were very hot, volatile objects, and they exploded in a short period of time, seeding the conditions for the next generations of stars to begin to form. We are just now acquiring the technology we think it will take to image some of these stars, to see the first pictures of these stars with our telescopes. Something like 9 billion years later, our star, the sun, and the various planets formed to make our solar system. Then over the next, say, 5 or so billion years after that, 4.5 billion years or so, life evolved on the Earth. And if you look at that image, all of human history is contained in approximately 1 pixel. Okay? In this sense, humanity has played a very insignificant role in our cosmic universe. In other ways, of course, we played the only important role. So there's nothing wrong with this timeline. It's fine. It's not wrong. But a cosmologist looks at this and they say, this is a really boring way to describe our universe's history. It's a terrible way to show it because all of the most interesting stuff happened way, way, way on the far left side, and you can't see it on this scale. So let's change the scale. Instead of showing it on a linear axis, let's do it on a logarithmic one. So now when you stretch everything out in powers of 10, you can look back towards much earlier times, closer and closer to the Big Bang. In particular, you can see the special moment about 380,000 years after the Big Bang when the first atoms formed. This transition was really important for lots of reasons I will explain, but the reason it happened had everything to do with the temperature of the universe. Today, our universe is filled with a background of radiation that's only 2.7 degrees above absolute zero. Very, very cold. But if you go back, you compress that radiation, the expansion of space done in reverse makes those photons shorter and hotter. And if you go back to this 380,000 year point, you find a point in our history where the whole universe was filled with a background of 3,000 degree radiation. This is comparable to the temperature of the surface of a red star, okay? But it filled all of space. This isn't just any old temperature, it's a particularly important one because it is what I like to call the melting point of atoms. What do I mean by that? I mean that if I took a box full of a gas of some particles, or some atoms, it doesn't really matter what kind, and I started to heat it up, right around the time they got to 3,000 degrees, the electrons would start to fall off. Instead of having a gas of electrically neutral atoms, you would have a plasma of electrons, protons, and other nuclei. So in our universe's history, prior to this transition, the universe didn't contain any atoms. It instead consisted of electrons, protons, and other nuclei. And then around 380,000 years, those electrons become bound to those nuclei, forming the first atoms in our history. The reason that cosmologists are so excited about this is that before that transition, when the universe was still a plasma, all of space was opaque to light. If you had a flashlight only 200,000 years after the Big Bang and you tried to turn it on, all those photons would just kind of bounce around. They wouldn't get anywhere. It'd be about as successful as if I tried to shine a flashlight through the Earth. It just wouldn't make it any distance at all. But as those atoms began to form, the space became increasingly transparent. And suddenly, a huge amount of light was liberated into space, and it's been traveling through the universe ever since, more or less unabated. Now, I'm a scientist, and intrinsically, in my heart of hearts, I'm a skeptic. If you want to convince me that something like I just described actually took place, isn't just a speculation, but that it really took place, you're probably going to have to provide me with some pretty compelling empirical evidence. Some sort of measurement or some sort of observation that I just think, okay, this clearly settles the matter at hand. And you might think that since this happened 13.8 billion years ago, evidence like that is just not going to be possible to acquire. After all, something so distant in the past, so far away, there's just no way we could plausibly measure that sort of thing. But in that respect, you'd be wrong. Because this is an image of that light that was released into our universe only 380,000 years after the Big Bang. We call it the cosmic microwave background. It was 3,000 degrees when it was released, but then as the universe expanded, those photons were stretched and cooled, and today it's that 2.7 degree radiation that fills all space. We're bathed in it right now. Every cubic centimeter has 411 or so photons from that transition. It's all around us. If you take an old television set, the kind with rabbit ears, and you turn it, well, at least in the States, if you turn it to channel 1 where there's no broadcast, maybe you have a channel 1 here, I don't know, you'll find that you just get this white static. Some few percent of that is coming from the Big Bang. This was measured for the first time or detected for the first time in the mid-1960s, and since then cosmologists have been eagerly measuring it with higher and higher precision. This is an image taken from the Planck Satellite, a telescope designed to study this radiation in particular, and it provides our highest resolution, most detailed map of this era of our cosmic history. Those tiny little blotches of orange, yellow, and blue you see is a depiction of the tiny little variations in temperature in this radiation. The hottest spots are about 1 part in 100,000 hotter than average. The coldest spots are about 1 part in 100,000 cooler than average. That maps on to a distribution of matter and energy that existed during the time when these atoms were forming. So by studying this, we know what our universe was like that close to the Big Bang, only a few 100,000 years after the origin of time. Let's go back to our timeline. Let's go back even further. This time we're going to go back to the first minutes and seconds after the Big Bang, where the first nuclei were forming. Prior to this time, the universe had things like protons and neutrons in it, but kind of like the melting point of atoms, it was too hot for the nuclei to bind together to form nuclei. But at this point, about 1 billion degrees in temperature, those nuclei began to undergo nuclear fusion. The way I like to think about this is that this was a point where the universe was so dense and so hot that the entire universe, all of space, functioned like an incredibly efficient nuclear fusion reactor. Doing the sort of stuff you find in the cores of massive stars today, except a lot faster because there were a lot more neutrons. Those protons and neutrons bound up into things like deuterium, tritium, helium-3, and eventually helium as we know it in the universe today. In fact, about 1/4 of all of the protons and neutrons found their way into helium during this period of time, along with a smattering of heavier elements like lithium and beryllium. We can use the equations of general relativity and some equations dictating the behavior of nuclear physics to calculate how much helium, lithium, and beryllium we think should have been formed in this way. And we can go out into the universe and try to measure it and see if we find those quantities. And we do. To the best of our ability to measure, this process of nucleosynthesis occurred in exactly the way the theory does. And that gives us a lot of confidence that we understand how our universe has evolved from the first seconds after the Big Bang all the way to the present. Let's go back even farther. Now we're going to go back to this point, something like a millionth of a second after the Big Bang. This is when the first protons and neutrons were forming. Before this point, there weren't any protons and neutrons. Instead, there were just the particles that make up protons and neutrons, things we call quarks, along with things we call gluons. A proton, after all, is nothing more than a few quarks held together by gluons, as is a neutron. As the universe cooled, these quarks began to bind together, forming the first protons and neutrons at an incredible temperature of about 10 trillion degrees. Now, when I described the formation of the first atoms and the formation of the first nuclei, I told you what we observed about from the early universe to kind of convince you that we knew this really happened. And in those two cases, we are quite confident they really happened. But we have no way of observing the proton and neutron formation epoch. We don't know of any way with current technology that enables us to see back to the first millionth of a second of cosmic history. But that doesn't mean we can't make any progress. What we do instead, what we have to rely on for the time being with our current technology, is to instead try to recreate the conditions that were found in our universe in these early times. And we do that using these fantastic machines we call particle accelerators. This is an image of the Large Hadron Collider. The Large Hadron Collider is an enormous 17-mile underground tunnel. Goes beneath the city of Geneva, Switzerland, and then it passes into nearby France. It's too big to fit under Geneva. And throughout that tunnel, we have 21st century magnets, super powerful magnets, superconducting magnets that accelerate protons to just under the speed of light. And when I say just under the speed of light, I mean 99.9999997% of the speed of light. I think I got the right number of nines there. Sometimes I get it one or two wrong, but awfully close to the speed of light. And then those beams of particles are directed head-on to each other in key locations inside these devices called particle detectors. They're roughly the size of a gymnasium, and they're all built of 21st century electronics. In those detectors, the particle beams collide, and about 600 million times every second, protons collide and their energy is transformed into new forms of matter and energy. The reason we do this, the reason we collide particles together, isn't immediately obvious. If I wanted to learn more about automotive mechanics, I don't get two cars and drive them into one another as fast as I possibly can. That would not be a very effective technique. But when it comes to particle physics, this is our best tool. We're taking advantage here of Einstein's most famous equation, E equals mc squared. What Einstein's equation really means is that mass is a form of energy. And if you put enough energy in one place at one time, you can convert that energy, at least in principle, to other sorts of things that carry lots of mass. So in the collisions at the Large Hadron Collider, we're able to create a large variety of particles in forms of matter and energy that carry a lot of mass that we don't find in our universe otherwise today, or at least not in any appreciable quantity. We produce things like top quarks and W bosons and Higgs bosons and tau leptons, and the list goes on and on and on. These particles are most of these particles are really rare in our world today, but a trillionth of a second after the Big Bang, the universe was teeming with them, all of them. That's because the kind of collisions that the Large Hadron Collider produces and we use to study are the kind of collisions that were going on a trillionth of a second after the Big Bang under those sorts of temperature and density conditions. This is a chart showing you all of the particles that we've observed and studied at the Large Hadron Collider and at other particle accelerators. In the upper left are the 6 quarks. The up and down quarks are the kinds that make up protons and neutrons. The others are more short-lived and exotic matter. The top quark was discovered at my own Fermi lab long before I worked there. In the bottom left are the 6 leptons. This includes the electron that's very well known and its heavier cousins, the muon and tau. There are also 3 neutrinos. The neutrinos are kind of exceptional because they're so feebly interacting that they can pass through the entire Earth without knowing it's there. But we can still study them. We know how to do that. And then on the right, we have the force communicating particles. For example, the reason that there's an electromagnetic force, the force that Michael Faraday presented here on this very stage more than a century and a half ago, that force exists, we now understand, because of photons being passed back and forth through space between charged particles. The gluon brings into existence a strong nuclear force, and the particles known as the W and Z bosons bring into existence the weak nuclear force. In the early universe, a trillionth of a second after the Big Bang, any particle that exists in space was constantly interacting with its neighbors in a flurry of activity, being created and destroyed in rapid succession, one after the other. An electron would become a top quark, which would become a gluon, which would become a photon, which would become a neutrino, and then all over again. It was an incredibly active time, full of creation, full of transformation, and everything we know about that period of time, we can thank the Large Hadron Collider and other accelerator experiments for helping us build and understand. Okay, so at this point in the lecture, you might be under the impression that I'm trying to tell you that we really understand a lot about our universe's first fraction of a second. But that's not true. We have a wonderful theory, a spectacularly successful theory. When we combine everything that Einstein taught us about space and time with everything we've learned about particle physics and quantum physics from particle accelerators and other experiments, we can explain a lot of what we see. We can explain the detailed patterns of light we see from the formation of the first atoms. We can understand how galaxies formed and clusters of galaxies and why they carry the kind of characteristics we observe. We can understand how the light nuclear elements formed only a few seconds after the Big Bang. But when we get to an earlier time than that, there are lots of reasons to think our theories may be incomplete or just wrong. For one, we can't observe those eras, so there's a lot of opportunity to get things wrong. And then secondly, there are a series of puzzles or problems that cosmologists have uncovered in the recent decades, which turn out to be really difficult to solve. And they all seem to point back to this early era. These puzzles make me, at least, suspicious that we've got it right. I don't know, maybe we'll tie up these loose ends as history progresses with better measurements and better observations, maybe a little theorizing. Or maybe these puzzles are indications that we've gone about this all wrong and we need to radically rewrite the first second of our universe's history book. Let me describe some of these puzzles that I'm talking about for you. The first of these puzzles has to do with the simple fact that matter exists in our universe. When we study matter at particle accelerators, we learn that every kind of matter is accompanied by something that's an equal and opposite version of that matter that we call antimatter. For example, the electron exists alongside something called a positron. They have the same mass, all the same properties basically, except that the electron has a negative electric charge and the positron has a positive electric charge. Quarks have their antimatter counterparts and antiquarks, neutrinos, antineutrinos, so on and so forth. There seems to be a perfect symmetry between the laws that describe matter and antimatter. You can't have one without the other. And, best we can tell, you can't create antimatter without creating alongside it an equal amount of matter. And you can't destroy antimatter without destroying an equal amount of matter. They come into and out of existence in unison. Their fates are intertwined. So, when cosmologists think about this, they run into a big problem. They have every reason to think, from the laws of physics as we currently understand them, that the early universe should have been filled with equal quantities of matter and antimatter. They follow the same laws of physics. Whatever created the matter would have created alongside it the same quantity of antimatter. But then, as the universe expands and cools, the matter and antimatter should have destroyed each other. But this would have left us in a universe without any electrons, without any protons, without any neutrons, without any atoms, without any stars, without any planets, without any galaxies, and without any life. That's clearly not the universe we live in. So we know we've got something wrong about how this played out in the early universe, but we don't know what the answer is. We have a bunch of guesses, but we don't know which one's right. The second problem also has to do with matter, but not the kind of matter that consists of atoms, something else. What I'm showing you here is an image of the Andromeda Galaxy. It's our nearest neighbor to the Milky Way. We can look at an object like that, and we can look at how many stars it contains, how much gas it contains. Basically, we can get a pretty good inventory of all of its visible matter. When we do that, we can work out, just using the laws of gravity, how stars should move around a galaxy like this. And you get something like this. This is a predicted rotation curve of a galaxy like Andromeda. As you move away from the middle of the galaxy, we find that stars should be moving in slower and slower orbits because they're farther and farther away from the concentration of mass. This is the same reason, basically, that Pluto moves in a really slow orbit and we move in a much faster one. It's the same basic idea. In the 70s, though, astronomers began to measure rotation curves that look more like this upper line. These galaxies seem to harbor a lot more mass than we could account for in terms of stars, gas, dust, and planets. Furthermore, the mass we couldn't observe seemed to be puffier, extending out to much greater distances from the middle of the galaxies. We had a lot of arguments and debates, but ultimately a consensus formed that what was going on here is that most of the mass in galaxies isn't made of luminous material. It's not made of things that appreciably radiate, absorb, or reflect light. Instead, it's made of something else, something that, for a lack of a better name, we just call dark matter. We don't know what dark matter is. Just because we can give it a name doesn't mean we understand it. Furthermore, as time went on, we became convinced that the dark matter must consist of one or more new kinds of substances, maybe some kind of new elementary particle or particles, that fill all space and basically interact under the force of gravity. If that were true, we could begin to understand how our universe came to have the structures in it that it does. This is a sequence of images taken from a computer simulation of dark matter particles, evolving from an early time shortly after the Big Bang on the upper left, and then in a sequence, allowing the universe to expand and the force of gravity to pull on the dark matter, collapsing it into things we call halos. When we look at the distribution of those halos in the lower right panel, we see a distribution that looks the same as the distribution of galaxies and clusters of galaxies in our universe today. So in a universe that's mass is dominated by dark matter, by which I mean about 5/6 of the total matter is made of dark matter, we can explain why the distribution of galaxies and clusters of galaxies in our universe look the way they do. So if you asked me 10 years ago what the dark matter was likely to consist of, I would have given you a pretty confident sounding speech about how WIMPs are the most likely class of candidates. WIMP stands for a weakly interacting massive particle. And we thought they were really compelling because if particles like that existed, then we could calculate how many would have been produced in the Big Bang, how many would have been destroyed, and how many would have survived. And lo and behold, the number that survived was about the right quantity you needed to explain things like this in those rotation curves of galaxies. So it left us thinking that that's probably the answer. It's pretty simple. It's really easy to write down a particle physics theory that behaves this way. That's probably it. And the better thing about it yet was that if it were true, we knew how to test it. We could build these really sensitive underground dark matter detectors. We knew how to do it, or at least thought we could figure it out. And, we thought in another, 5, 10 years, we'd discover this stuff. It was a no-brainer. So we went to deep underground laboratories, and when I say we, I mean the people doing experimental physics. They don't let me anywhere near the experiments for good reason. So this is an example of an underground laboratory in Italy, the Gran Sasso Laboratory. And in this little kind of chart, you can see xenon and dark side and Dama and Crest. All of those are dark matter detectors. And there are many others in other laboratories scattered around the world, and they have performed really well. Hats off to the scientists who built and designed these things, operated them. They have exceeded all expectations in terms of their sensitivity and performance. They are something like 100 million times more sensitive than they were when I started working on dark matter when I was a grad student. 100 million is a big number. But they haven't seen anything. No one can blame the experimentalists. Us theorists told them this is what you need to find, this is the kind of experiment you'd have to pull off in order to do it. They said, okay, we're up for that challenge. They went out and they did it. They did it well. But the things we told them to look for weren't there. Best we can tell, WIMPs are either harder to look for than we thought, and that's possible. I can write down some theories of WIMPs that can evade these constraints. I have to work a little bit, so it's a little harder than it used to be, but it can be done. Or maybe it's telling us that the dark matter wasn't produced in the early universe in the way we had long imagined. Maybe things played out differently in the universe. Maybe space expanded at a different rate. Maybe there were other forms of matter and energy present. Maybe dark matter's origin wasn't in this thermal bath like we imagined, but maybe it was produced in some other way. Any of those could be possible. And I would just say that the elusiveness of dark matter that's been surprising to me and others is at least suggestive of some events in the early universe we weren't expecting. That's not part of the standard story. All right, the third puzzle I'll talk about has to do with the rate at which space has been expanding over time. If you take Einstein's theory of relativity and deduce how an expanding universe should be changing over time, you wind up with predictions like this. Depending on exactly how much matter there is in the universe, it might be that it gets bigger for a while, reaches a maximum size, and then begins to contract, ultimately undergoing something like a Big Bang in reverse, which we call a big crunch. That's the lower line. It could also be, like in the upper line, the universe just gets bigger without limit, slowing down, but still steadily increasing in size as time goes on. And then there's kind of an intermediate case where it gets bigger and it kind of plateaus to a more or less maximum size ultimately. Those are all logical possibilities. And throughout most of the 20th century, cosmologists were out there trying to find out which of these universes we lived in. They thought of this as a multiple choice question, A, B, or C. In the 90s, we finally had the kind of telescopes it took to definitively answer this question once and for all. And what did they find? D, none of the above. That's approximately the sort of curve that we learned was the case. Indeed, right? All right, so in the 90s, we learned that space isn't just expanding. It's expanding at an accelerating rate. Space is expanding faster today than it was 1 billion years ago, and by all indications, it will be expanding even faster 1 billion years from now. This doesn't make any sense. It makes about as much sense as if I took a rock and I threw it upward and it just kept going faster away from the Earth. Something's propelling it. Gravity should be pulling on it, slowing it down. But it's not happening. The only way we have to understand this at all is if we posit that space itself contains, intrinsic to space, a fixed quantity of energy, a fixed density of energy. We call this dark energy. And that energy has to have about the same density at every place in the universe, and about the same density at every time in our universe's history. So that means as a cubic meter of space turns into 2 cubic meters of space as it expands, everything else gets diluted. All the matter's density goes down by a factor of 2. All the energy density in light goes down. And the energy density in dark energy stays the same. That means that over time, a bigger and bigger fraction of our universe's total energy is in the form of dark energy. And when it becomes the main component, accelerated expansion is predicted to take place. So today we think about 70% of the energy density in our universe is in the form of dark energy. We don't understand what it is. We certainly don't understand why it exists in the quantity it does. And I don't know how we're going to change that. All right. The fourth and final cosmological puzzle I'll mention is an effort to solve the fact that if I look as far back as I can in that direction with a telescope, and I look as far back in that direction as I can with the telescope, and I compare what I see, I basically see the same thing. Our universe on the grandest, biggest scales is remarkably homogeneous. Same amount of stuff everywhere, same temperature everywhere. In fact, the cosmic microwave background in that direction is within 1 part in 100,000 the same temperature as the cosmic microwave background in that direction. And it shouldn't be, because that part of space never had a chance to be in contact with that part of space. It's like 2 people who have never met or otherwise communicated with each other just wrote the same song. If you found 2 people who both claimed to have written the same song, you would say one of them, or both of them maybe, learned it from a common source. If you don't want to accuse them of being a liar, you say you heard it somewhere and it got in your head, subconsciously. But these people, these parts of our universe, never had a chance to meet or interact. In fact, from what we understand about the laws of physics, even if you traveled at the speed of light, that thing could never have contacted that thing. Just not possible. So to address this, we've been forced, and Alan Guth and others in the 1980s began to contemplate the possibility that shortly after the Big Bang, space may have had a period of hyper-fast expansion that we call cosmic inflation. The idea here is that you take 2 points in space in contact with each other, and you have them expand way, way, way faster than the speed of light apart from each other. That space grows so fast, it carries them to very different places, being driven by an energy field kind of like dark energy, but a lot more intense. And then that energy converts itself into normal radiation and particles, kind of starting off the Big Bang as we know it. And then you have an explanation for why that part of the universe and that part of the universe got to be so much alike. Because once they were neighbors. But you need something like this burst of hyperfast expansion that we call cosmic inflation if you're going to try to explain that. One particularly cool, in my opinion, facet or outcome of considering inflation is that it doesn't tend to end. If I have a piece of space and it's inflating, there'll be a little patch of it that stops inflating, and it gets filled with matter and energy, and it starts to expand like a normal universe, and it becomes a normal universe. But the rest of the inflating space continues to inflate, and then a patch of that stops inflating and makes a universe, and then another patch, forever. It never ends. You produce an unbelievably large number of universes in this way. So in other words, if inflation happened, we have every reason to think our universe is one of very, very many within a greater multiverse. I wouldn't say a multiverse is a scientific fact. That's certainly not true. But the more we learn about inflation, the more likely it seems to be that our universe is one of many. All right, so let me pivot a little bit here. We have an incredibly successful theory. We can explain the details of the cosmic microwave background, the expansion history of our universe, and the formation of light nuclei. We understand this stuff really well. And yet, there are these puzzling loose ends. Dark matter, dark energy. What happened to all the antimatter? And why did cosmic inflation happen? All of this stuff are kind of the impossible or really challenging, outstanding questions that we've been struggling with for the last years and decades. And as time goes on, they haven't proven to become easier. If anything, the experiments we've done have only made these questions more difficult to address. So when I want to frustrate and or entertain my colleagues, I like to ask them the following question. And they'll come back to this. It will seem like a departure, but it will come back to this in a moment. I like to ask them what they think it would be like to have been a physicist in 1904. Why 1904? I could have picked any year, I think. But no, 1904 is special. 1904 was the year that physicists had the greatest confidence in their ability to understand the universe. At that point, Newtonian physics had been successful for 200 years. New discoveries kept being made, like electricity and magnetism and heat and other things like this. And from the Newtonian mindset or paradigm, we kept being able to tackle it. We explained more and more with these ideas of mass and force and acceleration and velocity and geometry of space. All the stuff that was introduced by Newton 2 centuries earlier just kept working. And most physicists, the vast majority of physicists in 1904, were confident that the Newtonian framework would continue to thrive into the distant future, maybe forever. Of course, there were a few loose ends in 1904 as well. One of those loose ends had to do with the nature of light. It had been measured that light always travels at the same speed in any frame of reference. That's different from other kinds of waves. If I tell you there's a water wave moving across the ocean at 20 miles an hour, and I put myself in a boat moving along with the wave at 10 miles an hour, I'll measure the wave to be moving 10 miles an hour in my frame of reference. Everyone expected light to be like this too. But it turns out that light travels at the same speed, 3 times 10 to the 8 meters per second, in every frame of reference. And no one could understand why. The second of these puzzles had to do with the planet Mercury and its orbit. Like any other planet, Mercury moves along an ellipse, and the orientation of that ellipse changes a little bit from year to year. It precesses. Over the course of the 19th century, the precession of the perihelion of Mercury was measured very accurately. The rate at which it precessed was measured very accurately, and it was just a little bit different than what Newton had predicted. Best we could tell, Newtonian physics didn't accurately describe Mercury's orbit. Now, one hypothesis that was popular at the time is there might be some other planet out there, something called Vulcan. That's where the name came from. And maybe it was just tugging gently on Mercury, screwing up its orbit a little bit, but astronomers looked for Vulcan and they didn't find it. No one had a good explanation for why Mercury was behaving the way it was. Perhaps the biggest outstanding problem had to do with the sun. In fact, physicists could not explain how something the size of the sun could be emitting so much sunlight for so long. For billions of years, this thing had been putting out about the same amount of energy in sunlight. We knew that from geology. But even if the whole sun were made of gasoline or coal, it should have run out of fuel after only a couple of tens of thousands of years. People also imagined that maybe it was contracting, converting gravitational potential energy into sunlight, but that would last millions, not billions of years. So no one had a clue why the sun was doing what it was doing. And then lastly, physicists had no way of even approaching the problem of how atoms worked. Atoms were known to give off these peculiar spectral lines, these kinds of light. No one knew why. No one could even begin to calculate it. Furthermore, when we tried to calculate what an electron should do in an orbit around a proton, we found that those electrons should spiral inward and crash into the nucleus in almost no time at all. In other words, atoms shouldn't be stable. And yet here we are. Of course, these didn't turn out to be loose ends. In 1905, Einstein came out with a sequence of incredibly revolutionary papers. He introduced the theory of relativity, and he wrote the first paper introducing some of the ideas that would eventually become quantum physics. These papers didn't build upon the Newtonian paradigm. They tore it down and built up something else in its place. The theory of relativity explained why speed of light was the same to all observers and all frame of references. It's because space and time were not the way that Newton imagined them. The general theory of relativity offered E equals mc squared, which could explain how the sun could convert a very small fraction of its mass into enough energy to power sunlight for 10 or more billion years. The theory of quantum physics that Einstein's work started off could explain not only the spectral lines we observed from atoms, but why they were stable. And eventually, Einstein's general theory of relativity would explain with high precision why Mercury's orbit behaved the way it did. So, I find myself asking the following question. Is 2020 the 1904 of cosmology? We have a wonderful theory, it's been successful for a long time, and yet there are things we cannot explain, at least haven't been able to so far. Maybe it will turn out that these are just loose ends that we will neatly resolve with further observation experiment, or maybe we will find out that the only way to resolve these lingering problems and puzzles is with a new paradigm, one that I can't even imagine what it looks like yet, because it hasn't been written. All right, thanks. This has been a lot of fun. I look forward to taking a bunch of your questions.
Let's hear your questions.
Roughly how long did the first stars live for?
Yeah, so I think the answers we're not exactly sure, but probably millions of years. So that sounds like a long time, but a star like the sun will last for about 10 billion. So it's a lot shorter than the stars we have today.
Right, next question. How about over there?
Very good question, by the way.
Shirt.
If we live in a multiverse, does that mean that the beginning of the universe we live in might not be the original Big Bang, but just our particular universe at a later time?
So if we live in a multiverse that was a universe that was created through the process of inflation, we have every reason to think, now we have an incomplete theory of inflation, but we have every reason to think that inflation would have continued forever, spawning universes forever. So we could be anywhere along that line. It's possible that inflation never even began, but just is a continuous process for infinitely far back in time. It's only speculation, but that seems consistent to me. It's even, I'll hesitate to say this, but it's even possible that you could imagine a universe like ours going on to eventually have another inflationary age in the future that created the inflationary phase that eventually created our universe.
Right. Any questions on this side, maybe? Yes, over there. Just wait for the microphone. There should be one coming. Oh, sorry to make you run. I dispatch side to side, but and I'll come to you upstairs in a minute, so get ready. Just over here.
Hi. So if the universe is constantly expanding, what will happen if eventually the galaxies get so far apart that light can't reach us anymore?
Yeah, the future of our universe is kind of a bleak one. So we have this cosmic horizon beyond which nothing can reach us. And that's just going to get closer and closer and closer. Like 100 billion years from now, we'll be in a state, well, first of all, the Milky Way and all its kind of nearest neighbors will have all merged by then into one giant galaxy. And we won't be able to see anything else. That will be the only thing we can see when we look in the night sky. So right now, I give you these pictures and they're galaxies galore, right? 100 billion years from now, there will be nothing like that. If dark energy is truly constant and it never changes, that will be kind of the end of the story. If it increases even a minuscule amount faster than that, so if it's not really constant but increases slightly with time, which is still possible, then even that super galaxy will get torn apart as space continues to expand. Ultimately, the solar system would get torn apart. Of course, our solar system won't live that long, but solar systems will. And eventually things like planets will get torn apart into individual atoms. And then those atoms will get torn apart all the way down to the smallest subatomic particle. So it's going to be a hard place to live in the end game.
All right. Do you have any questions from upstairs? Yes, just...
How does supersymmetry link to the constant expansion of the universe?
Wave your hand so I can see who I'm talking to.
Over there.
Oh, in the top. I didn't even know there was a...
top.
Okay, right. So supersymmetry is a theory that's been hypothesized since the 70s. There's been a ton of interest in it. I'm one of many, many, many people who've written a lot of papers on supersymmetry. It's one of these theories that looks just so good and solves so many problems all at the same time that even before you observe any evidence of it, you think, oh, this has got to be true. What it predicts is that for all particles fall into one of two categories. They're either a boson or a fermion. The quarks and leptons are all fermions, the others are all bosons. And according to supersymmetry, nature can't have one without having the other. So you take the electron, it's a fermion. It says there has to be a supersymmetric partner of it that's a boson. We call it a selectron or superelectron. It has the same electric charge and same other characteristics. It might have a different mass. It does have a different mass if it exists. And then you have the photon, which is a boson. It has to have a fermionic counterpart. We call it the photino, so on and so forth. Supersymmetry is great, except for the fact that we've never observed any of those supersymmetric particles. I thought it was pretty likely that the LHC would turn on and we'd discover them for the first time, or at least some of them, but it hasn't. Maybe it will in its next run. But I think it's fair to say that whereas supersymmetry was super popular 10 years ago, its popularity is waning now. People are a lot less confident supersymmetry is real. How it connects to cosmology is that supersymmetry provided us with one of our very best or favorite preferred dark matter candidates. The supersymmetric partner of particles like the photon, Higgs bosons, and Z boson all become things called neutralinos. And those neutralinos have all the characteristics you want in a dark matter candidate. They just work really well as dark matter, but we haven't seen it. Neutralinos probably aren't the dark matter now, although there's still a sliver of hope.
Excellent. Do you have a question on this side, maybe, just to mix it up? Up over there, maybe? Yeah.
So you know how you said it would look the same if everything was expanding as if it was all shrinking at the same time?
Right.
How do we know it is expanding and not shrinking?
Well, I think, strictly speaking, we don't, okay? I'm going to put my philosopher of science hat on now. I'm going to even posit that there's no difference. Two theories which in every possible respect predict all of the same things aren't different theories. There's just two ways of thinking about the same thing. Now, bear in mind, though, the theory where everything is shrinking in unison, I really mean everything. That's a lot of things to kind of coordinate. So the speed of light has to be shrinking. The forces that hold protons and neutrons together in atoms, they have to change in just a way to cause the atoms to shrink at the same rate. And those have nothing to do with each other. So it's quite a coincidence. And I could list many other things that all have to shrink or change in the same rate to mimic the effects of the expansion of space. So if I had to speculate which one of these is really going on, I would say that space is expanding. For one thing, Einstein's theory says it has to be. But I won't quibble with you too much if you insist on saying all of the material in the universe is shrinking instead.
Right. You have a question? Right. Microphone's coming.
You were saying that protons and neutrons were created in a fraction of a second after the Big Bang. But why weren't atoms heavier than iron formed then? Surely there was enough energy around at that time to create all atoms.
Good. So there's plenty of energy. That's not the problem. The problem is there's so much energy there that if you drop the iron nucleus into it, it would fall apart. Iron is way too fragile to survive the first millionth of a second after the Big Bang. So the first time that our universe really had the conditions that could make something like iron were in relatively early stars, not the very first stars, but stars not long after that, that through nuclear fusion, you could slowly build up heavier and heavier nuclei. Iron has so much binding energy, it's the end state of a lot of cores of stars today.
Just a question about the scale of dark matter. I understand the idea of you can detect dark matter because of Andromeda and the spinning of the outer solar systems. Would it affect at all the rotation of Pluto? Because that was found by looking at the rotation of things and being able to pinpoint it because of that before they knew anything about dark matter.
So the best place to look for signs of dark matter is where there's not a lot of mass in normal matter. The solar system is not that. The solar system, by definition, has a star in it. And that means it's in an abnormally high density region of normal matter. So the sun just swamps any dark matter that would be here. We just can't detect it. If it were here, we wouldn't know. So we assume we're being bathed in dark matter right now, but we can't empirically tell one way or the other.
When you say we have an incomplete theory of inflation, how incomplete is it? Because we seem kind of vaguely confident that it happened, but we don't really know kind of the ins and outs.
All right, yeah, let me expand on that a bit. So I think we have good reasons to think that inflation or something like inflation probably happened. That's about as confident as I'm willing to be. There are really good cosmologists, smart people who are studying this sort of thing for a living who would disagree with that. They would say, no, inflation's got deep problems. Here's my other theory that I offer instead. The consensus view is that inflation's our best theory, but very few of us will say we're certain that inflation happened. When inflation was predicted in the 80s, it made a number of fairly specific predictions about the patterns of light we would see in the cosmic microwave background. I'll use a little bit of technical jargon here, but we predicted, or it was predicted at the time, that those temperature variations would be adiabatic, Gaussian, and nearly scale invariant. Don't worry about what those three words mean, but all three have turned out to be true. For that reason, many cosmologists who were originally skeptical of inflation have come around to thinking that probably happened. That's about all we know, okay? If you pick up a review article in a journal on inflationary theories, it will list in theory after theory after theory after theory. They took place at different points in the early universe. They involved different kinds of energy fields or particle content, and they ended in different ways. So there's a huge array of possibilities. We're slowly testing them with observations. And I would say in the next 10 years or so, observations of the cosmic microwave background are pretty likely to measure some important stuff that allow us to narrow that search. For example, we're going to measure something called B-mode polarization, or at least we hope we are. This has not been measured in the cosmic microwave background to date, but if we do measure it, we'll be able to tell you how high the energy density was during an inflation. That would be an incredibly powerful number to have. Also, we're looking for something called non-Gaussianity, which should be really small in inflation, but not precisely zero. So if we were to measure that, again, we could narrow the range of models down dramatically and also be more confident that inflation really took place.
Right. Do you have a question from above? Yes. Balcony.
Hi. What's your opinion on the discrepancies in the measurement of the Hubble constant?
So when we measure the Hubble constant in kind of our cosmological neighborhood, we get one number, about 73 kilometers per second per megaparsec. And when we use the cosmic microwave background and other early time measurements to infer what we think the value of the Hubble constant should be based on that, we get a number that's not 67, not 73, but more like 67. These are really different because the error bars on those two measurements are so small that they both can't be right. It's possible that somebody's just measuring it wrong. In fact, probably that's the most likely answer, and that will get resolved in the years ahead. It's also possible, and I've been working on things like this, but it's possible that there were other forms of matter and energy present in the first hundreds of thousands of years of our universe that would change how we infer the Hubble constant from that early time data. And it could change it enough to bring these two numbers into approximate agreement. And that's what I'm cheering for. That's what I'm hoping is going on. I'm hoping there's some sort of energy density that we don't currently know about, some new kind of particle species that was abundant then that skewed things just enough to bring these two numbers into alignment.
If there's a multiverse, then is it possible that the multiverse could have had a Big Bang as well?
Sure. If we had a multiverse that came into existence through inflation, it's possible inflation just continued in forever in all directions of time. It's also possible it started. Maybe there's a Big Bang that took place at a singularity in space-time, the kind that Stephen Hawking used to talk about. And that happened once. And right after that, inflation started. And that led to the multiverse, including our universe. That's a totally consistent picture. But I'll warn you, there are a lot of consistent pictures. We don't really know. Good question.
How do you measure time in an inflationary universe?
Yeah, so the kind of people who work on inflationary theories have several kinds of time in their theories. There's something called conformal time, and then the kind of time we might talk about. So it turns out to be a kind of a nuanced question. That being said, there's nothing preventing me from hypothesizing something like a clock, okay? Some sort of timekeeping device. Maybe it's a particle with a certain half-life, and I watch how much of it decays. And over the course of inflation, I see how much of it decays, and I use that as my measuring device. That's perfectly consistent. One can do that. So yeah, I think the answer is the same way you would measure time or talk about time in any other physical context.
You were saying that you look one way in the universe and the other way they have the same results because they were very close together at the beginning. How could you possibly explain them not being able to talk to each other without massive inflation? Because otherwise...
So in other words, what you're asking, what other theories are there to compete with inflation?
How could you separate those two particles so after 13.8 billion years they couldn't have talked to each other?
So one kind of alternative to inflation that has some serious challenges and hasn't been very successful yet, but smart people are thinking about it, are cyclic models or bouncing cosmology models. These are models where the universe expands, stops, contracts, bounces, and expands. That means in the past, everything was in contact at some point in cosmic history, solving this problem.
But sorry, I still don't understand how, if they were in contact, but then they had light travels fairly quickly, how could they not have spoken to each other through light in all that time?
Sorry, I misunderstood your question. I apologize. So it's simply a matter that if, let me put it this way. We're surrounded by a horizon. We can't interact with anything outside of that horizon. And we never could, and we never will, okay? That point, horizon reaches just about to where I am now. And that point's horizon reaches to just where I am now. They are both outside of each other's horizon. So they never had a possible opportunity to interact. Light couldn't travel that fast. Nothing could.
But I guess that's where I'm coming from.
Yeah.
So they were close together at some stage.
In inflation, they would have been. But in the standard Big Bang theory, they never were. Let me one more thing. So people think that in the standard Big Bang theory, that the universe was very small at some point. That need not be true. It could be that our universe goes on forever in every direction. It's infinite in scope. And in the past, we could go back to a point a few 100,000 years after the Big Bang, and everything was 1,000 times closer than it is now. But still infinity. And I go back arbitrarily farther, and everything's closer and closer and closer. It doesn't mean that point was ever close to that point. And even if they were kind of close, they were only close for such a short period of time that light can't travel very far.
Right. Just 2 rows down right here.
In regards to the matter-antimatter imbalance, do you have any hypotheses as to what would have caused it?
Yeah, I do. But the reason you should take it with a grain of salt is that if you find any particle cosmologist, they will have written their own theory too. And most of us aren't right. Yeah, I wrote a paper like 15 years ago positing it was actually a supersymmetric theory to build on the other question before. I think, in fact, the theory I wrote down to explain it is now falsified. The LHC didn't see the particles we said would exist, so we weren't right. But that's okay. We're in good company. I will say that we kind of know what sort of things have to be in any theory that will do this. These conditions were laid out in the 1960s by the Soviet physicist Andrei Sakharov. He worked out that any theory that could explain this problem introduces some new kind of interaction we'd never observed that changes the net number of protons and neutrons, or quarks if you prefer. Also, we know that those interactions have to happen in a way that favors antimatter becoming matter over the reverse. Okay? Otherwise, the two processes would just wash each other out. And we know these interactions must have taken place in a particularly volatile setting. Maybe there was some sort of dramatic phase transition that happened in the early universe while these interactions were at play. Maybe there was some kind of heavy particle that stopped interacting with the bath of particles around it, and then waited a while, and then spontaneously decayed to produce mostly matter and not as much antimatter. Those are the sorts of things that might have been responsible. But yeah, no one really knows.
Can you say anything at all about the few seconds before the Big Bang?
So here's the trick, okay? When we talk about the moment of the Big Bang, the space-time singularity at time equals 0, this isn't some arbitrary point on a timeline. This was the first point in the timeline. Asking what happened before the Big Bang is like asking where on a map is north of the North Pole. It's not a cogent answer to that question. If you read the work of Hawking and Roger Penrose, they actually proved in using general relativity and from certain kinds of principles involving quantum physics that if you run those equations backward far enough, you will reach the space-time singularity where time and space kind of become like each other, okay? And they have a boundary, a curved, smooth boundary. There's nowhere you can go on that manifold of space-time that gets you before t equals 0. That's why I don't talk about before the Big Bang. I want to say, though, that we know so little about the early universe that I find it conceivable that everything I'm saying about that era of time will be overturned one day. But to the best of our current understanding, what I'm telling you is the consensus view.
Yes, please go ahead.
So on the our standard model, you've explained 3 of the 4 fundamental forces. So why has gravity of why can't we find the fundamental force or the reason for the fundamental force of gravity?
Yeah, let me go to that chart for you. Here we go. All right, so on the right side are the particles that communicate the force of electromagnetism, the strong nuclear force, and the weak nuclear force. Gravity is conspicuously absent. That's because we don't know how it works on a quantum level. There's probably some quantum force carrier that communicates gravity, call it the graviton. We've never seen a graviton, and frankly, we don't have a clue how one would ever see a graviton. It'd be a very hard thing to test. And we do know that when we take what we know about quantum physics and we combine it with what we know about general relativity, at least one of these theories is broken, at least insofar as you can't apply it to arbitrarily high energy conditions. One or both of these theories breaks down, and presumably these 2 theories get replaced by some grander, more complete theory, call it a theory of quantum gravity. Maybe it has something to do with string theory or loop quantum gravity. I don't know. I certainly don't know. I don't think anyone knows. And that theory will address all these questions. But it's not on this chart because this is a chart of things we've observed, things that we can study, things that we understand. And quantum gravity is not among such things.
Right. I'd like to hear a question. If you're sitting there, I think I have a question, but it might be silly, it might be a stupid question. Usually these are the absolute best questions, so don't hesitate. Raise your hand. Who has such a question? How about here? Let's hear a question.
It's a question about black holes.
Excellent.
What happens inside one?
What's inside one?
Yeah. What happens in there?
Excellent. We need to make him work for this.
I'm not sure I'm going to exactly answer your question. I'm going to say some things like adjacent to your question. All right, so we know how to make a black hole. All you need to do is put enough mass and energy in one place at one time. General relativity will do the rest. All a black hole is something that has so much energy and mass, or just think of it as mass, I guess, that it curves the space around it so dramatically that the curvature reaches infinity, and even light can't travel in or out. Okay? When very massive stars explode as a supernova, the thing that's left behind collapses into a black hole. We also know that every galaxy, or just about every galaxy, has at its core a supermassive black hole. Like our Milky Way has a galaxy in its core that's a few million solar masses, a few million times as massive as the sun. Some even have bigger black holes than that. We're starting to have an understanding of the quantum nature of black holes. Hawking showed a long time ago that the information stored in a black hole is proportional to its surface area. It was a little weird. You should think it's volume, right? If I take a box of gas, the information stored in that is proportional to its volume. But black holes are different. That has led to a series of ideas involving holography. The idea that things like two-dimensional physical theories can be identical to other seemingly very different three-dimensional theories. So that raises the question, is our four-dimensional space-time really a five-dimensional other theory that we can't even put our heads around? And as far as what's in a black hole, there's something called the no-hair theorem, which says that other than the mass and charge and rotational rate of a black hole, there's literally nothing else that distinguishes one black hole from another. So if that's true, then you really can't say anything at all about what's inside a black hole. That information's been erased forever from the universe somehow. Or maybe it's encoded on its surface, depending on how you think about it. Jason, close enough?
Right.
If there was a space-time...
Singularity?
Yeah, that's what I was about to say. I just forgot my words. If there was a space-time singularity with infinite density, then two or three questions. One, why do we not live in an infinitely dense place today? Two...
Let's focus on maybe on this one, or just pick your favorite one, because
how can something have an infinite density and still a physical appearance? It is there, but not nothing, but infinitely small.
Yeah. So one thing I learned as a physicist a long time ago is not to lean against fragile things, is that just because something seems really counterintuitive and seems like it can't be right, doesn't mean it's not real. If I insisted that everything about our universe kind of follow my intuition, kind of make sense in my gut, I would have never accepted the theory of relativity. I never would have accepted anything I currently know about quantum physics. Those things are so weird, but that's how the world is. So, could there be an infinite temperature and density space-time singularity that started off the Big Bang? It seems really far-fetched to me too, but that doesn't mean it couldn't be true. And Hawking and Penrose showed that if you take a space-time like ours and you let it evolve backwards, that's what you get. So maybe that's the answer, but I want to caution you, We don't really know. Nothing that happened in the first second we're really sure of, and certainly nothing that happened at t equals 0, if there ever was a t equals 0, is something we can say with any confidence actually took place. Good question.
All right, we have time for one more. How about right over here?
All right, last question, make it a good one.
No pressure.
No pressure.
Towards the beginning, you said that the universe in its first seconds is about 3,000 degrees Kelvin, and now it's about 2 degrees Kelvin. Is there a chance it's ever going to reach 0 Kelvin, and what would happen then?
So, if I take one photon, okay, traveling through space, and I stretch that space, so I double it. I double the length of that space. That will double the wavelength of that photon, which will cause its energy to go down by 2, and the temperature of any collection of photons as part of to go down by a factor of 2. So if I make the universe 1 billion times bigger in linear dimension, then that 2.7 degree Kelvin will become 2.7 divided by 1 billion Kelvin. To reach true 0, of course, would require you to expand to an infinite length, some infinite time in the future, but we will asymptotically get closer to that temperature of 0 as space continues to expand.
Well, that's something to look forward to.
Yeah, cold death.
So there were still lots of hands up. We're running out of time, but I have a great solution. On the way out, you might be able to pick up a copy of Dan's book, which might very well answer your burning questions. Otherwise, Dan will be hanging around outside there signing books, and I'm sure you can approach him with any further questions. So all that's left to do is to thank Dan for a wonderful evening and talk.
Hi everyone. It's a bit of a change to actually have a live audience. Welcome to Sky for the Month for February 22. For the newer members who've never been to these before, this is just a bit of an overview of what's happening over the next month before the next meeting. So those with telescopes, if you want to get them out and have a look at something, hopefully you'll find something in here worth looking at. Right, we've already gone on to the highlights for the next month. We have a full moon on the 17th, which is tomorrow night. So anyone wanting to have a look at the moon, put your sunglasses on, look through your telescope. Tomorrow morning, Mercury is at its greatest elongation. Basically means it's as far from the Sun, or the angular distance between the Sun and Mercury is at its maximum. But at the moment, Mercury is a morning object, so if you want to see Mercury, you'll have to get up before dawn. Last quarter moon occurs on the 24th. You see a couple of comets mentioned there. I won't go into detail now. I'll do cover them a little bit further on. There we go. Voice is kind of muffled. Okay, so new moon on the 3rd of the 3rd. Another thing, Jupiter in conjunction on the 6th of the 3rd. On the 6th of the 3rd. Now, when Jupiter's in conjunction, it means it's on the other side of the Sun. So it's not in a position to be viewed either morning or night time. Later on in the month, it will actually pop out and be a morning object, probably until about the middle of the year, or just after the middle of the year. Mars, 1 degree north of Pluto. Now, the big issue there is you can see Mars, but you can't see Pluto. But 1 degree is, if you hold your arm at a full length there, the width of your thumb is about half a degree. So 2 thumb widths to the north of Mars is Pluto. So if you put a big enough telescope on that, and you find a little dot 1 degree north of it, that'll be Pluto. So probably the best way you have any hope of finding it without taking a series of photographs and seeing which one moves. And Uranus, which is another one. It's about 5.5 magnitude Uranus, so it's another one that really needs a telescope to look at. So it's right on the edge of, if you've got the vision of a 10-year-old, you might be able to see it on a really dark night, but for most of us, would need a telescope. And it's 1.5 degrees, so 3 thumb widths to the west of the moon. Now, because it's a new moon on the 3rd and that's on the 7th, you're really only going to have a sliver of the moon. Alright, not even first quarter at that stage, so it's not hopefully going to dominate view of Uranus. And on the 13th of the 3rd, Neptune's in conjunction. Probably not going to worry too many of you because you definitely need a telescope to see Neptune.
Can I ask a question here then?
Yeah.
You said Mars is 1 degree north of Pluto.
Yes.
Or am I reading it wrong when you said Pluto is north of Mars? Pluto will be
Mars is 1 degree north of Pluto.
Mars.
So Pluto would be 1
south.
degree south
That's
of
what I was
Mars.
picking up on, that was all, or
Yeah.
whether I've misunderstood.
Yeah. I guess it depends. I reckon they'd put Mars being 1 degree north of Pluto because you'd be able to find Mars. And then if you move to the south of Mars, which would be back this way, you should be able to find Pluto. Problem is with Pluto, it's in Sagittarius at the moment, which that's where the galactic centre is, and so there's a lot of other objects up there as well. The sky looking to the south, your south celestial pole there in octans. Been a few of us trying to find that with our NEQ6s and various ways to try and get a decent alignment for our telescopes. But for those who just plonk their scope down, basically point it to the south, there's plenty to have a look at down there. You've got the Southern Cross here. When you put a telescope on eight crux there, you'll actually see two points of light. It's a double star. And an interesting feature just below it there, below the bottom one, is the jewel box. And these are good targets for viewer astronomers to have a go at because they're actually quite easy to find in a telescope because you've got a good star to actually star crawl off. Other stuff, you've got the Tarantula Nebula, which is in the Large Magellanic Cloud. So most people use astrophotography to pick that one up. It's one that's favoured by the astrophotographers to look for. And sorry, I'm standing delay there. And I think the amazing part of that is it's actually in another galaxy. It's not even in our own galaxy. So once you pick that one up, you've got something that you definitely know is outside of our galaxy. Another one or two worth looking at. Am I kind of pushing the right thing? Over here you've got 47 Tucana, which when I first turned it on, you saw that globular cluster. That's 47 Tucana. It was a photo I took of it out here one night. Rather pleased with it, so it's now on my desktop. And the other one, obviously, is Omega Centauri, and both of them are far enough now above the horizon. They're also visible to the naked eye. Well, Omega Centauri it looks like a little fuzzy patch. 47 Tucana, not quite that good, but it's actually quite easy to find by these 3 stars of Hydrus, or these stars here from the Tucana, and you can actually see these stars quite, well, I won't say they're fantastically clear, but you can actually see them with the naked eye and pick them out quite easily. Point your telescope there, you look through your finder scope, the fuzzy patch is the globular cluster. So I'm pointing a lot of these out at the moment because we've got the TLD on Saturday. Hopefully you're going to bring your telescopes along, and there's certainly some objects for you to have a look at. Oh, wrong way. Okay, so how to practice. We're having to do it by voiceover. Looking to the north, couple of things there. We've got Orion in the sky now, which is probably just as well because planetary-wise it's a bit of a boring time. Most of them are in the big ones are all in about the same part of the sky, so at the moment they're not in the ideal viewing position. But favourite one that's very easy to get because it's visible with the naked eye is M42, which is the Orion Nebula. And a lot of people, a lot of astrophotographers, that's one they tend to favour and have a crack at to start with. You can see through your telescope. You won't see colour through your telescope. It'll appear as a white fuzzy cloud. Okay, and that's it's not the limitation of your telescope, it's a limitation of your eye. Other various things, open clusters up in Cancer. Cancer is not a very bright constellation, but Leo is. And if you look, you can pick these stars here very easily. The Nebula and Regulus are quite easy to pick. Okay, so you've got these, well, just a little further towards the west along the ecliptic plane. That dotted line there is the ecliptic, which is the path that planets, the moon and all that sort of stuff apparently follow fairly close to. Alright, so the planets themselves, Mercury has just gone through its inferior conjunction, which means it's passed between the Earth and the Sun. So why didn't we get a Mercury transit? That's because a different angle between the Earth and the Sun, it didn't actually pass directly between us. It's a fairly rare event, so if you ever see a Mercury transit coming up, try and get hold of a solar scope. Towards the end of January, it returns to the morning sky. So if you want to see Mercury, it is visible to the naked eye, usually fairly low on the horizon. And if you look at it through a telescope, generally you'll see it in phases like the moon. Both the inner planets do the same thing as what the moon does. You get the crescent and depending on where it is in its orbit, up to full. I've had the shakes. On the 17th of the 2nd, so tomorrow night, or tomorrow morning, it reaches its maximum elongation, as I said earlier. That's when it's furthest away from the Sun, and that is the best time to view it, if you're keen on getting up in the morning. Okay. Towards the end of the month, 6 lower on the horizon has a close encounter with Saturn, about 2.5 degrees or 5 thumb widths away from Saturn. And actual fact is there's a bit of a interesting, not really a conjunction because there's still a bit of a gap, but 4 planets are going to be in one constellation, which I do actually cover a bit later on. And Venus is one of the other ones. All right. Mercury orbits the Earth in 88 days, or orbits the Sun in 88 days. So it's only every 22 days to travel through a quarter of its orbit, which before you know it, it'll be a morning be an evening object again. Venus has reappeared in the early morning sky in Sagittarius. It's there with Mars, and we'll be there with Saturn and Mercury as well. So you'll have the 4 planets all in reasonably close proximity. The only downside is you probably need to get up around about 3 or 4 a.m. Earth, summer ends and autumn begins at the end of the month. Oh. And I'll fix that one. Alright, Mars is quite visible in the eastern morning sky now. It's well through its opposition, its conjunction, so it's risen up. It will appear with Venus about 5 degrees apart, so about 10 thumb widths. About that. So not all that far apart. On the 8th of the 3rd, Venus, Saturn and Mercury all within the constellation of Capricorn. Now Capricorn's not a very bright constellation, so the brightest objects in that constellation are the planets. Jupiter, very low in the western sky now, If you look out there, right on dusk, you might just see it in the evening twilight. Not a very good position for viewing. It does head into conjunction a little after Saturn. Saturn is in conjunction on the 5th, so those two planets really not in good viewing position at the moment. Uranus is still found in the northwestern evening sky. It's very close to the 6 magnitude star 29 Arietis, which is Aries, and if you look at, you can find both of them. Uranus is the green one, and Neptune is lost. It's approaching its conjunction as well. So what that essentially means is the 4 gas giants, or 2 gas giants and the 2 ice giants, are all in the same part of the sky. So at the moment, all the planets are over. Got a rebel, isn't it? All right, moving on to the planets. This is basically how they appear. Now, because Mercury's just gone through its inferior conjunction, we're looking largely at the back of it, which is why we see the unlit part of it. As it moves to greatest elongation, you'll see about half of it. So it does appear as phases. Venus is moving towards its inferior conjunction, and you're only getting the crescent of it, but it is very close to us, so it's actually still quite bright, quite a good object for your telescope. I find Venus is the sort of one to view, or best viewed, while you've still got a little bit of daylight, because it helps mute it down a little bit, because it is very bright, and with a dark sky behind it, it tends to be a little difficult to focus. Saturn still has its rings tilted towards us. We'll do until 2025, when it'll be in a position with relative to the Sun that will actually pass through what's known as the ring plane, and Saturn won't have any rings. That occurs every 15 years, and that's because its orbit period's about 30 years. Jupiter, these planets, when you can see them, they're always pretty specky and that sort of stuff, very easy objects to get.
Try standing on it.
Uranus and Neptune, I'm really not sure what they look at it like that. I've never seen them quite that big, and I'm looking at them through a 10-inch telescope. So the best you can usually do with Uranus and Neptune, because there's not a lot of features on them, is pick the colour of them. Okay, so Uranus, slight greeny blue colour, and Neptune is quite a distinct blue colour. Other stuff, quite a few comets, as you can see at the moment. Put these up there because these are good targets, once again, for the astrophotographers. There is one there, Comet Borrelly, or Borrelly, not sure how you put it, but it's about 8th magnitude, which is quite bright for a comet. It's in Pisces and sits around about mid-evening, reaches its perihelion, or reached its perihelion on the 2nd of this month, and then it'll move into Aries. Comet Leonard, which is the one we were all looking at just prior to Christmas. It was in a very good position. It was right next to Jupiter, so it was fairly easily found and photographed. It's faded now to about 11th magnitude because it's on its way back to the Oort cloud, or wherever it heads out to. Comet Cow-2 can be found in Cetus, which is the whale. Moving into Taurus. Taurus is fairly easy to find, and Aldebaran is the brightest star in Taurus. So it ends the month, February, fairly close to Aldebaran, but it will also fade to about 11th magnitude, so definitely a telescope object. Comet Pan-STARRS is brightening, it's on its way in. It's now 10th magnitude, so a little bit better than the 11th ones, but it's a pre-dawn sky object in Ophiuchus, which is sort of in the vicinity of Sagittarius and Scorpio. Comet Atlas, visible for most of the night sky in Gemini. Gemini is fairly easy to pick by the twins, Castor and Pollux, and it's around 10th magnitude, but it's fairly low on the northern horizon, so you'll need a reasonably good northern view to see it. And Comet Kopf has just started to appear. It's in Sagittarius, also means that it's a morning object as well. So, yeah, one for all the early birds, and it's currently about 11th magnitude. And meteor showers, we've got the Alpha Centauri exactly from 28th of January till the 21st, so not much longer to go. It did have its maximum around the 8th, and apparently quite a few. So best time to probably see meteor showers is just after midnight. And the reason for that is that's the direction we're heading, so we tend to run into the meteors rather than running away from them. And highlight, next Saturday, starting at 4 PM, Telescope Learning Day. I'll be doing the talk, which I have modified from last year, because last year I sort of felt it was too much what you were looking at, not enough on telescopes, and now it's more on telescopes and those sorts of things. Those not attending the talk, lawns will need a mow and that sort of stuff. Just generally look after the site. The presentation, barbecue, which will take the form of a Bunnings style barbecue, obviously because of COVID issues, that sort of stuff. And for those who've got a telescope and want to learn how to use it, by all means bring it. There'll be someone here who can show you how to get the best out of it. All the information tonight was provided by Astronomy 2022. Not sure if there's any still available now. We do have some for sale, or did have some for sale. So check with Simon for a lot more information than I've put up there. Any questions?
I have a question with a statement.
Sorry,
this is how he's talking. Back in the 1960s, I used to spend quite a bit of time looking for Venus during the day. And it's not a bad exercise. What you do is well, back in the 60s, what we used to do is look at the rising and setting times in the age. Now the age still has the rising and setting times, so you can still get the information, which means then you could work out when it transits
about where it is. Yeah.
So if you can locate your north-south line, you can find out when it's transiting the meridian, and get a pair of binoculars, and sure enough you can pick up Venus, even at the moment. As I say, it's a good exercise because you're having to work out where the meridian is and get some sort of estimate as to what angle it is up the meridian and so on.
It makes it a bit easier if you know the angle of the ecliptic plane on any given particular time too. So
obviously,
it's
yes.
normally there, but generally the arc will run from east to west, and it just depends on where we are in our year as to whether it's a shallow arc or whether it's a steep arc.
When Venus is a very thin crescent, and that's when it's virtually in alignment with the Sun, you can actually see it with the naked eye and in fact see its size. So you can actually see the crescent shape.
Okay. Yeah,
but you've got to be there at the right time and the right day virtually.
All right.
Can I just add a little sort of thank you, because I'm a bit of a newbie, so I get excited over seeing everything for the first time. So I came in on Saturday night. It was great because there were only 4 of us, and it was just fantastic. I mean, I've not seen things like the jewel box, and it was incredible. And it was, again, really interesting that that there was another fellow who kept sharing, looking, and he couldn't see the colours that I was seeing. And so we just learned so much about that, you know, just your own eye and different eyes and practiced all that sort of thing. And we had the international station going around, so we all decided as little kids watching that. So, you know, I mean, there's not a lot of societies that sort of operate on a Saturday night at 10 o'clock and you can come and see this stuff. So I've had heaps of discussions with friends since. It's just terrific, you know. So it's very, this really is a very good group. And the ghost of Jupiter, we spent a lot of time looking at that. How long's that around? Well, never mind, I've too many questions. Oh, just the rings of Saturn then, when if we sort of lose track for how long, roughly, do you, in that cycle,
about twice every orbit, isn't it, that they go edge on the rings of Saturn?
22 years. What's that like?
Yes, it just becomes the,
Saturn's orbit's about 30 years.
30 years.
Yeah, just under the 30. Jupiter's about 12 years.
Right.
So if you work out how far Jupiter travels in a year, it's about twice as far as Saturn. And so I've lost track of years with COVID, but was it 2 years? No, not this year just gone, but the year before that. So just over a year ago, both Saturn and Jupiter were very close together.
So have we just finished the best look at Saturn's rings for a while? Or
until later in the year, then it'll go around the sun and come out the other side.
Yeah. Right, okay.
In actual fact, it's the orbit of the Earth that puts them into conjunction and opposition, because we're actually going faster than they are. So essentially, your sun's there, Earth is here, and as we move around, you'll have Jupiter out here, but as we move around here, Jupiter apparently moves in behind the sun. That's essentially how it works. It'll then, once we pop out the other side, it becomes a morning object until we get around to here, and as we get around to here, it will start moving into each couple of weeks, or each week or so, it will start to move into the pre-midnight sky and that sort of stuff, and then we'll have it for a while, and then once we move past, so it's us whizzing past it every so often. So if you take note of where it is now, next year it'll be about 30 degrees in half further around. So a little bit of an exercise if you ever want to try and predict where it'll be.
Being stuck here on Earth at the bottom of this enormous gravity well really sucks. The amount of energy it takes to escape into the black would make even Captain Reynolds curse up a Gorham storm. But gravity is a funny way of evening the score, giving and taking in equal measure. And there are special places in the solar system where the forces of gravity nicely balance out. Places that a clever and ambitious solar system spanning civilization could use to get a toehold on the exploration of the universe. These are known as the Lagrange points, or Lagrangian points, or libration points, or just L points. They're named after the French mathematician Joseph Louis Lagrange, who wrote an essay on the three-body problem in 1772. He was actually extending the mathematics of Leonard Euler. Euler discovered the first 3 Lagrangian points, even though they're not named after him. And then Lagrange turned up the next 2. But what are they? When you consider the gravitational interaction between 2 massive objects like the Earth and the Sun, or the Earth and the Moon, or the Death Star and Alderaan, actually strike that last example. As I was saying, when you've got 2 massive objects, the gravitational forces balance out perfectly in 5 places. In each of these 5 places, you could position a relatively low mass satellite and maintain its position with very little effort. For example, you could park a space telescope or an orbital colony, and you need very little or even 0 energy to maintain its position. The most famous and obvious of these is L1. This is the point that's balanced between the gravitational pull of 2 objects. So for example, you could position a satellite a little above the surface of the moon. The Earth's gravity is pulling it towards the Earth, but the moon's gravity is counteracting the pull of the Earth, and the satellite doesn't need too much fuel to maintain position. There's an L1 point between the Earth and the moon, and a different spot between the Earth and the sun, and a different spot between the sun and Jupiter, etc. There's L1 points everywhere. L2 is located on the same line as the mass, but on the far side. So you get the sun, Earth, L2 point. Now at this point you're probably wondering why the combined gravity of the two massive objects doesn't just pull that poor satellite down. Now it's important to think about orbital trajectories. The sun is here and the Earth is orbiting around it. So the satellite at that L2 point will be in a higher orbit and will be expected to fall behind the Earth as it's moving more slowly around the sun. But the gravitational pull of the Earth pulls it forward, helping to keep it in a stable position. Now, you want to play a lot a Kerbal Space Program to really wrap your head around it. And sadly, your No Man's Sky time isn't helping you at all, except to teach you that hyperdrives are notoriously finicky and you'll never have enough inventory space. L3 is located on the direct opposite side of the system. Again, the forces of gravity between the two masses balance out so that the third object maintains the same orbital velocity. For example, a satellite in the L3 point would always remain exactly hidden by the sun. Now hold on. I know there's a million thoughts going around in your brain right now, but bear with me. We'll get there. Now there are two more points, the L4 and the L5 points. And these are located ahead and behind the lower mass object in orbit. You form an equilateral triangle between the two masses, and the third point of the triangle is the L4 point. Flip the triangle upside down, and there's L5. Now, it's important to note that the first three Lagrange points are gravitationally unstable. Any satellite or another Earth positioned there will eventually drift away from stability. So they need some kind of thruster to maintain this position. Imagine a tall, smooth mountain with a sharp peak. You put a bowling ball at the very top. So you're not going to need a lot of energy to keep it in that position. But the blowing wind will eventually knock it down out of place and down the mountain. And that's L1, L2, and L3. And it's why we don't see any natural objects located in those places. But L4 and L5 are actually stable. It's the opposite situation. We're a deep valley where the bowling ball will tend to fall down into it. And we actually do find asteroids in the natural L4 and L5 positions of the larger planets, like Jupiter. There's the Trojan asteroids trapped in these natural gravity wells through the gravitational interaction of Jupiter and the Sun. So what can we use Lagrange points for? Well, there's all kinds of space exploration applications, and there's already a handful of satellites in the various Earth-Sun and Earth-Moon points. Sun-Earth L1 is a great place to station a solar telescope, where it's a little closer to the sun, but can always communicate with us back on Earth. The James Webb Space Telescope is destined for Sun-Earth L2, located about 1.5 million kilometers from Earth. From there, the bright Earth, Sun, and Moon, they're all huddled up in this tiny location in the sky, leaving the rest of the universe free for observation. Earth-Moon L1 is a perfect place to put a lunar refueling station, a place that can get to either the Earth or the Moon with minimal fuel. Perhaps the most science fiction-y idea is to put a huge rotating O'Neill cylinder space station at the L4 or L5 point, being perfectly stable in orbit and relatively easy to get to, and it would be the perfect place to begin the colonization of the solar system. Well, thanks, Gravity. Thanks for interacting in all the strange ways that you do in creating these stepping stones that we can use as we reach up and out from our planet to become a true solar system spanning civilization. Thanks to gravity, there are places across the solar system which are nicely balanced. They're called Lagrange points, and they give us the perfect vantage for a range of spacecraft missions, from observing the sun to studying asteroids and more. Various spacecraft have already visited Lagrange points, used them for some or all of their missions, and there are fascinating plans in the works that could put new missions and even space colonies into these balanced places in the solar system. Let's explore the Lagrange points. I'd say roughly half the questions I get from viewers are about Lagrange points. Okay, maybe that's a bit of an embellishment, but seriously, this is a topic you're fascinated about. Why do we use them? Which Lagrange points work best for which missions? Could there be planets hiding in Lagrange points behind the sun? No. So today, I thought I'd begin a series on the solar system's Lagrange points. How have they been used practically in the past by various space missions, and what are the clever ideas that have been proposed to use them? Today, we'll focus on L1. But before we get into that, let's do a quick refresher on the Lagrange points. Thanks to gravity and orbital mechanics, there are 5 relatively stable spots in space in relation to 2 massive objects. So, the Sun and the Earth have 5 Lagrange points, the Earth and the Moon have 5, the Sun and Jupiter have 5, etc. Let's use the Earth and the Sun for an example. L1 is at a point in between the Earth and the Sun. Without the gravity of the Earth, an object at this point would be faster in its orbit and drift away from the Earth, but the Earth's gravity pulls it back a bit, keeping it stable. L2 is on the far side of the Earth at a distance of about 1.5 million kilometers. Same deal. An object there would be in a higher orbit, moving slower than the Earth, but the gravity of the Earth tugs on it to keep it in line. L3 is on the opposite side of the Sun, at almost the same distance the Earth is from the Sun. And there are 2 additional Lagrange points, L4 and L5, and these lie ahead and behind the Earth in its orbit by 60 degrees. The L1, L2, and L3 points are meta-unstable, which means that you can't just park a spacecraft there. Imagine a rock sitting at the top of a hill. You could keep it balanced with a little bit of effort, but once it starts rolling down the hill, it's hard to stop it. Any spacecraft that goes to these points needs to be constantly firing its thrusters to get back to this stable point. L4 and L5 are stable, so now imagine a rock sitting at the bottom of a valley. If you push it up the side of the valley, it wants to roll back down. So if you can park a spacecraft into one of these Lagrange points, it'll remain there forever without fuel. But you can only get these stable points if the mass ratio between the 2 objects is greater than 24.96. The Sun is 332,000 times more massive than the Earth, so that qualifies. And the Sun is 1,048 times more massive than Jupiter, so again, that works. But Pluto and Charon, for example, are too close in mass to generate L4 and L5 points. There are a couple of other things to note. First, the Lagrange points only work when the 3rd object has a negligible mass compared to the mass of the bigger objects. So, Sun, Earth, and spacecraft, or Sun, Jupiter, and small asteroid, but you can't have Sun, Earth, and another Earth. Also, Lagrange points aren't actually points, they're more like regions. Consider how planets and moons follow elliptical paths as they orbit. This means that the exact location of the stable area is changing over the course of an orbit, and a spacecraft will need to use up even more propellant to keep in a stable location. Okay, there's your explainer. In this episode, we'll consider the L1 Lagrange point, how it's been used in the past, and some clever ideas to take advantage of this spot for future missions. Let's start with the Sun-Earth L1 Lagrange point, a point located about 1.5 million kilometers closer to the Sun than the Earth. This is the perfect spot to put a spacecraft that needs to constantly observe the Sun without the pesky Earth or Moon getting in the way, or observe the daytime side of the Earth, or both. This is the location of NASA's Solar and Heliospheric Observatory, or SOHO. The spacecraft was launched in December 1995 and was originally only supposed to observe the Sun for 2 years in its main mission. Well, here we are over 24 years later, and SOHO is continuing its observations, although it's down most of its instruments. SOHO isn't exactly in Sun-Earth L1. Nothing really is. It actually orbits around the region, completing one circuit every 6 months. Other sun-observing satellites, such as NASA's Advanced Composition Explorer and the WIND satellite, are also at L1, making observations of the Sun. The first spacecraft to actually use L1 was the International Sun-Earth Explorer 3, which was launched to the region in 1978. Its job was to watch how the solar wind interacts with the Earth's magnetic field. Several other spacecraft have used this point as well. NASA's Genesis mission collected samples of the sun's solar wind by loitering around in this region before returning back to Earth in 2004. ESA's LISA Pathfinder mission was also sent to the L1 Lagrange point in 2015. The purpose of LISA was to demonstrate the underlying technologies that will go into a future space-based gravitational wave observatory with multiple spacecraft flying in formation. Inside the LISA spacecraft, there were 2 gold-platinum cubes which were kept in a constant state of freefall inside the spacecraft, isolated from the forces except for gravity. The spacecraft then used thrusters to keep itself centered around the cubes while a laser continuously monitored the distance between them. I'll talk about other gravitational wave observatory ideas in the next episode. NASA's Deep Space Climate Observatory, or DISCOVER, is also located at the Sun-Earth L1 point. From this vantage, it can continuously monitor the sun's solar wind, giving us advanced notice of coronal mass ejections. And then, it can also see the sunlit side of the entire planet Earth, watching changes in ozone levels, volcanic eruptions, and weather systems. So these are the missions that have used the L1 Lagrange points in the past. Next, I'm going to talk about some future mission ideas that I hope will blow your mind. As we've already discussed, the Sun-Earth L1 Lagrange point is the perfect spot to continuously observe the Earth, and one idea is to use this as a place to observe asteroids. One of the problems with asteroid observation is that astronomers can't see the space rocks flying towards us through the glare of the sun. NASA's NEOCAM mission would send a space telescope to the Sun-Earth L1 point to continuously observe as much of the sky as possible, looking for hazardous asteroids. From this vantage, it would be able to see asteroids as close as 45 degrees to the sun. Within about 4 years, it could find 2/3 of the potentially hazardous asteroids out there. If all goes well, the spacecraft could launch in 2021. There have been some fascinating ideas to use the Sun-Earth L1 Lagrange point to slow down climate change. Researchers have proposed using a single large sunshade, or a giant Fresnel lens that would distort the light from the sun. Here's the idea I like the best, proposed by Roger Angell from the University of Arizona. It's mega engineering at an absurd scale. He estimates that it should be possible to launch a cloud of tiny spacecraft into the L1 point and use them to block some of the light from the sun. Each spacecraft would measure about 1 meter across and weigh only a gram. Instead of being a single enormous sunshade that needs to push back against the light pressure from the sun, millions would orbit in a vast cloud about 100,000 kilometers across the L1 point. They wouldn't need to do station keeping. They'd just orbit around the L1 region like a swarm of bees, slowly falling out of orbit and getting replenished as necessary with replacements. It would take a total of 20 million tons of these spacecraft to make a difference, and they could be constructed by dismantling a metal asteroid, or spending a few $1 trillion in SpaceX Starship launches. With this cloud, we could dim the sun enough to counteract the contribution of carbon dioxide in the Earth's atmosphere. Although trillions of dollars sounds like a lot of money, we might get to the point where it makes sense to spend that kind of money to get the problem under control. And that makes me sad. I'll put a link to the paper in the show notes, and I highly recommend you give it a read. It's absolutely fascinating, and then chase down anything else Roger Angell has proposed. Mars sucks. It's cold, dry, and has a thin atmosphere, but we could use the Sun-Mars L1 Lagrange point to fix it. In a proposal from Jim Green, the chief scientist at NASA, we could position an artificial magnetosphere shield at the L1 point in between the Sun and Mars. This would block the solar wind, which is constantly tearing away at the Martian atmosphere and blowing it out into space. This would allow trace gases to build up in the thin Martian atmosphere, thickening it up to the point that the carbon dioxide poles would sublimate, further thickening the atmosphere. The greenhouse gases would warm the atmosphere further, and even the trapped water would start melting during the Martian summers, adding even more water vapor into the Martian atmosphere, warming it up even more. Over time, you could restore up to 1/7 of Mars' original oceans just by blocking the solar wind. Another place that could really use a sunblock is Venus. In fact, it might be the only way to make that planet habitable. If you could position a sunshade at the Sun-Venus L1 point that's 4 times bigger than Venus, you could block the radiation from the sun. Its atmosphere would slowly cool down over the centuries to the point that the carbon dioxide freezes out and falls as snow. Then you could use various chemicals to bind up the carbon dioxide before you let the planet warm up again. Closer to Earth, we've got the Earth-Moon L1 point, which is located about 85% the distance from the Earth to the Moon. This is a spot that's balanced above the Moon and would make the ideal place to conduct lunar activities. Although NASA has chosen a different orbit for the Lunar Gateway, L1 would work too because it's easy to reach the surface of the Moon from this spot. Astronauts on board the station would remain over the same spot of the Moon, able to operate rovers and mining equipment with almost no latency. But at the same time, they'd have a constant communications link with the Earth. An L1 station could serve as an off-Earth facility for testing samples of other worlds without risking any kind of contamination with Earth. A spacecraft there could also observe the entire planet Earth, but unlike geostationary satellites, the Earth would rotate through its point of view, allowing it to observe the entire planet every day. But one of the most ambitious ideas would be to have an Earth-Moon L1 point be the top of a space elevator, leading up from the surface of the Moon. You've probably heard of the idea of a space elevator from Earth, but the problem is that we don't have strong enough materials to support the pull of the cable from the Earth into space. But the pull of gravity on the Moon is much lower, and so a lunar elevator could be made with composite materials that we have today. Imagine mining robots on the surface of the Moon that transfer lunar regolith and helium-3 to a lunar elevator that carries them up to the L1 Lagrange point. From this point, it takes very little propellant to transfer the material to another spot in the solar system, or maybe to that cloud of satellites you're constructing to block the light from the sun and slow down climate change. Back to our Sun-Earth system example. L2 is the one that's on the far side of the Earth, about 1.5 million kilometers more distant. L3 is on the opposite side of the Sun, about the same distance that the Earth orbits. I know it's backwards, but I'm going to tackle L3 first. That's because it's much easier. There's pretty much no practical use for L3 that we can think of, and spacecraft have never used it. Because it's unstable, you couldn't park another planet behind the sun and keep it permanently hidden. For 2 reasons. The first, as I mentioned in the previous episode, is that the third object needs to have negligible mass compared to the other objects in the system. You could have the Sun, Earth, and a spacecraft, but not Sun, Earth, and another Earth. If an Earth-sized planet did magically appear in the L3 Lagrange point, it would only remain there for about 150 years before the instabilities in the system, Earth's elliptical orbit, and the interactions with the other planets would cause it to drift out and eventually crash with us. Venus actually gets within 4.8 million kilometers of the Sun-Earth L3 Lagrange point every 20 months or so. Another downside to L3 is the fact that it's on the far side of the Sun, so you can never directly communicate there from Earth. Any mission in Sun-Earth L3 would need to use another spacecraft as a communications relay. Nobody's ever used the spot, but is there any practical use for it? One idea is that the far side of the Sun would be a good spot to do ongoing observations of the Sun from an angle that we can't observe here on Earth. We could watch the near side from Earth and then the far side from an L3 spacecraft and create a 3D map of the entire Sun. This was proposed in a 2009 paper titled Spacecraft Trajectories to the L3 Point of the Sun-Earth 3-Body Problem. The paper is mostly about the interesting orbital dynamics that it would take to reach this point, and not a compelling argument for why we might go. NASA's twin stereo spacecraft, currently drifting ahead and behind the Earth in orbit, already give us a view of the Sun's activity from a vantage point that we can't get here on Earth. In thrilling 3D. By 2001, they were generating complete images of the surface of the Sun. I hinted at one other idea in an episode about using a powerful laser system that could send a laser sail spacecraft to another star system. It might be difficult for the nations of the world to build a petawatt laser which could also be aimed at the Earth. Put it on the far side of the sun where it can never be directed our way. Just because we have 5 Lagrange points doesn't mean we have to use them all. Okay, on to L2, which is incredibly practical and filled with spacecraft. In fact, I don't have enough time to catalog all the missions that have been or will fly there. The Earth-Sun L2 Lagrange point is a spot located about 1.5 million kilometers past the Earth away from the Sun. It's meta-unstable, and like L1, it's more of a region than a specific spot, thanks to the Earth's elliptical orbit around the Sun and the gravitational interactions from Jupiter and the other planets. For a space telescope, the 3 brightest objects in the sky are the Sun, the Earth, and the Moon. By positioning at L2, you're able to keep them all together in one tiny region, giving you a view to the entire universe with minimum interference. As Carl Sagan said, that's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. It's fine, I guess. I just don't need that in my telescope. I think that's what he said. The first spacecraft to ever travel to Sun-Earth L2 was NASA's Wilkinson Microwave Anisotropy Probe, or WMAP, launched on June 30th, 2001. It flew to the L2 point and then spent almost a decade mapping out the cosmic microwave background radiation, the afterglow from the Big Bang that we can see in all directions in the sky. WMAP provided astronomers with the most precise measurements of the temperature of this background, allowing them to better estimate the age of the universe as well as calculate the amounts of dark matter and dark energy that make up the cosmos. By 2010, WMAP had run out of fuel to keep itself positioned in the L2 point, and the mission was ended. It's now orbiting around the Sun, slowly getting farther and farther away from the Earth in its own heliocentric orbit. The next spacecraft to go to L2 was NASA's WIND spacecraft. This spacecraft is currently located at the L1 point, constantly observing how the Sun's solar wind interacts with the Earth's magnetosphere. But after launch, the spacecraft first flew out to the L2 point in 2003, where it studied the magnetosphere at the far side of the Earth, before returning to Earth and then flying out to the L1 to study at this angle. Next came the European Space Agency's Herschel Space Observatory. This was a 3.5 meter diameter infrared telescope launched in May 2009. It was actually the largest primary mirror ever launched into space, 4 times bigger than any previous infrared telescope and 1.5 times even bigger than Hubble. Using its infrared instruments cooled down to almost absolute zero, Herschel was able to peer through the dust and gas that surround newly forming stars, watching the conditions where new planets can form. Herschel was able to look farther out into space and further back in time than any other infrared observatory, seeing how galaxies formed in the early universe. Herschel ran out of fuel in 2013. The mission was wrapped up and the spacecraft joined WMAP, orbiting the Sun forever. Then came ESA's Planck Space Observatory, the successor to WMAP, making even more detailed observations of the cosmic microwave background radiation. Launched in May 2009, Planck arrived in July and began producing a survey of the entire sky in microwaves. The full survey of the sky was released in 2013, giving astronomers an even more detailed measurement about the background temperature of the universe, refining their estimates about its age, amounts of dark matter and energy, and mapping out the polarization of light. The mission wrapped up in 2013, and the spacecraft was shut down, drifting away from L2 into heliocentric orbit. One of my absolute favorites is ESA's Gaia mission, and we've done a whole episode on this amazing telescope and its task of mapping out more than 1 billion stars in the Milky Way. The spacecraft was launched in 2013 and will continue mapping out the Milky Way until 2022. By the end, it'll have created a 3D map of the Milky Way, charting out the positions and movements of more than 1% of the stars of our galaxy, as well as finding asteroids, extrasolar planets, and exotic objects like white dwarfs and neutron stars. I promise there'll be many more updates from Gaia over the coming years. The most recently launched mission to L2 was Russia and Germany's Spectre RG, which took off in July 2019. This is an X-ray observatory designed to map out the high-energy regions of the universe. It should be able to detect new galaxy clusters because of the hot gas generated by galaxy mergers, as well as finding new supermassive black holes. We've talked about boring L3, the history of Sun-Earth L2. We're going to shift our gaze to the Earth-Moon L2 point, as well as the future missions planned out for all these regions. When James Webb does fly, it'll deploy a tennis court-sized multi-layered sunshade that blocks the light from the Sun and Earth, allowing it to cool its instruments down to almost absolute zero. Then it'll use its enormous 6.5 meter beryllium primary mirror coated in gold to observe the universe in the infrared spectrum. It will be able to look out right to the edge of the observable universe, seeing the first stars and galaxies that formed after the Big Bang, and watch as they come together in larger and larger structures. It'll see through the dust and gas that shrouds newly forming stars to reveal protoplanetary systems, and it'll be able to directly observe the atmospheres of extrasolar planets, helping us to understand what conditions are like on other worlds and if they could be habitable. Because James Webb is flying to L2, the clock is ticking. It'll only be able to make observations for about a decade before it runs out of propellant and drifts out of L2, joining the previous spacecraft in the heliocentric orbital graveyard. Engineers did install a docking ring on James Webb, so who knows? Maybe they'll send up a mission to give it a longer lifetime. Right after James Webb comes ESA's Euclid, due for launch in 2022, a visible and near-infrared telescope going to the L2 point. Euclid will look out into the universe, mapping the speed that galaxies are moving away from us to a distance of about 10 billion years in the past. From these observations, astronomers will be able to create a more precise calculation about how fast the expansion of the universe is accelerating thanks to dark energy. Then comes WFIRST, another infrared telescope. Unlike James Webb, with its narrow field of view, WFIRST is a wide-field telescope observing huge regions of the sky to map out dark energy. It will also continue the work started by NASA's Kepler Space Telescope to find extrasolar planets. It'll use gravitational microlensing to find new planets, watching how the light changes as stars pass in front of each other, revealing planets in the signal. It'll also directly observe planets, blocking the light from the star with its onboard coronagraph. The White House has tried to cancel WFIRST every year, and Congress has funded it every year, so no guarantees it'll ever fly. ESA has even more missions they're planning to L2 over the next decade. There's the planetary transits and oscillations of stars, or PLATO, which will directly observe terrestrial planets in the habitable zone of sun-like stars, and I go into more depth on this mission in another video. The Atmospheric Remote Sensing Infrared Exoplanet Large Survey, or ARIEL, will also go to L2 and use this spot to observe 1,000 known exoplanets using the transit method, as well as studying their atmospheres and chemical composition. And it might be bringing along a smaller Comet Interceptor mission that would loiter around in the L2 point, waiting for a long-period comet or interstellar object to fly out and intercept. Another is the Advanced Telescope for High-Energy Astrophysics, or ATHENA. This will be an X-ray observatory designed to scan the skies for the high-energy radiation blasting out from galaxy collisions, supermassive black holes, and exotic objects like neutron stars. It'll have 100 times the sensitivity of the most powerful X-ray observatories launched already. L2 is going to be a busy place, and I'm really just scratching the surface. Before we wrap up this episode, let's shift over to the Earth-Moon L2 Lagrange point. This is the spot that's about 15% farther than the distance from the Earth to the Moon. There aren't a lot of uses for this spot, but the Chinese Space Agency used it as part of their Chang'e 4 mission to the Moon in 2019. The lander and rover were sent to the far side of the Moon near the southern pole, which means that they couldn't communicate directly with the Earth. China launched the Chichao satellite in 2018 to the Earth-Moon L2 point to communicate with the Chang'e 4 mission, relaying their scientific data back to Earth. But the most studied purpose of the L2 point would be as the location for human missions to the moon and deeper into the solar system. The L2 point is at a spot that's nearly out of the Earth's gravity well, where you can travel to other regions in the solar system with a very small change in velocity. This was originally considered to be the location of NASA's upcoming Deep Space Gateway, but it was revised to a halo orbit that brings it closer and farther from the moon. A space station at L2 could serve as an exploration platform for astronauts to travel down to the far side of the moon, as well as operate rovers remotely, especially the South Pole Aitken Basin, which seems to contain vast amounts of water ice. An astronaut operating a rover from L2 could drive twice as fast as someone controlling it from Earth through a relay satellite. Sun-Earth L2 is the perfect location to put an infrared telescope, as it can remain colder and farther from the sun. And it's easy to keep the annoying sun, Earth, and moon all in one tiny location in the sky, so you can contemplate the rest of the universe. Earth-Moon L2 is great for communicating and exploring the far side of the moon, as well as a jumping-off point into the rest of the solar system. In our next episode, we'll look at L4 and L5, the stable spots that share orbits with various worlds. All right, let's talk about L4 and L5. While the previous L1, L2, and L3 points are located along a line that connects the two masses, L4 and L5 orbit with the less massive object, maintaining a position 60 degrees ahead and behind. And unlike the previous points we talked about, L4 and L5 are metastable, which means that a spacecraft can loiter in the area without needing to use any fuel at all. In fact, it's a gravity well that a spacecraft needs to fight to escape if it wants to. As with the previous points, it's important to remember that any object in L4 and L5 needs to have insignificant mass compared to the two massive objects. Astronomers call natural objects hanging out in these regions Trojans. So, in the case of the Sun and Jupiter, you can have a pretty hefty asteroid hanging out in these points. In fact, the most massive Trojan asteroid discovered so far is 624 Hector, measuring about 225 kilometers across and having a mass of 9 quintillion kilograms. And many smaller asteroids have been detected in this region as well. For the longest time, astronomers knew that the Earth had trapped dust in its L4 and L5 points. But in 2010, NASA's Wide Field Infrared Survey Explorer, or WISE, discovered the first actual Trojan asteroid lurking in this region. Designated as 2010 TK7, the object measures about 300 meters across and traces an unusual orbit that moves above and below the Earth's orbital plane. In fact, WISE was able to discover the Trojan in the first place because it has such an unusual orbit that carries it quite far afield from the L4 point, and normally the Sun obscures our view into this region. Astronomers have also discovered dust in the Earth-Moon L4 and L5 points, known as Kordylewski clouds, but so far, no actual asteroids. Astronomers have found Trojan asteroids sharing Neptune's orbit, Uranus, and even Mars has its share of Trojans, which astronomers think might have formed out of ejected material from an ancient collision with Mars. Astronomers think that the largest Mars Trojan, 5261 Eureka, was blasted out of Mars more than 1 billion years ago, and that it was spun up over eons to the point that fragments were ejected into new but similar orbits. So clearly, nature has figured out how to use the L4 and L5 points. But what about spacecraft missions? Actually, so far, no mission has ever been sent to these regions. No Sun-Earth L4 missions, nothing to Jupiter or Mars. There, the history portion is over. So what about the future? Are there any clever ideas to use them? You bet. At the 46th Lunar and Planetary Science Conference, astronomers proposed that a CubeSat mission be sent to one of the Sun-Earth L4, L5 regions to search for additional Trojan asteroids beyond 2010 TK7. Equipped with an infrared camera, this CubeSat mission would be able to perform a comprehensive survey of the region, tracking down many of the larger Trojan objects. From this, astronomers would be able to identify potential candidates for future robotic orbiters and landers. Depending on their inclination to the Earth's orbit, they would require very little change in velocity to reach from Earth, which means they'd be inexpensive energy-wise. We could get a lot of science done with not a lot of spacecraft. Another mission that's coming together is NASA's Lucy mission. Lucy will spend 12 years visiting 7 different asteroids, 1 in the main asteroid belt, and then 6 in Jupiter's Trojan regions. Its flight path will carry it on several slingshot maneuvers past Earth to gain speed, and then it'll fly out to Jupiter's L4 region in 2025, visiting 4 asteroids, including a double asteroid. Then it'll fly back to Earth, slingshot out to the L5 region, and visit another asteroid in 2033, and then it'll fall back down into the inner solar system again. Of course, Lucy will be equipped with a standard array of remote sensing instruments to study the geology, surface composition, and physical properties of all the asteroids it flies past. In the last episode, I mentioned that there's no good use for the Sun-Earth L3 point, but there's actually one idea that might use L3, L4, and L5 to build a gigantic gravitational wave interferometer called the Astrodynamical Space Test of Relativity using optical devices, or ASTROD. Astronomers are already planning the LISA Observatory to fly in the 2030s. It'll consist of 3 spacecraft flying in an equilateral triangle formation, 2.5 million kilometers apart from each other. And it'll detect gravitational waves with more sensitivity than the best Earth-based instruments. The ASTROD plan would take this to the next level, building a gigantic equilateral triangle by positioning a spacecraft at L3, L4, and L5. Each arm of the instrument would measure 260 million kilometers across, and by timing their movements, they could remain within about 20,000 kilometers of this distance at all times. A gravitational wave interferometer this big would be 260 times more sensitive than LISA, able to detect collisions between supermassive black holes, intermediate mass black holes, compact binaries, and even the gravitational wave vibrations left over from the Big Bang, a time that we can't see with optical wavelengths. A laser interferometer the size of the Earth's orbit. That would be pretty cool. These are some of the missions to explore the L4 and L5 regions, but I know what you want to hear. You want to know about the massive rotating space colonies proposed by Gerard O'Neill in the 1970s. The most science fiction use of Earth-Moon L4 and L5 Lagrange points has got to be the O'Neill cylinder space settlements, proposed by Princeton physicist Gerard O'Neill in the 1970s. The concept came out of a 10-week program in engineering systems design at Stanford and Ames Research Center in 1975. More than 24 scientists, students, and professors came together for 10 weeks to design how a future space colony might work, allowing people to survive and even thrive in the harsh environment of space. The O'Neill cylinder would be a giant rotating space station measuring 1,800 meters across and be a home for 10,000 people. And to keep it in a stable location, they proposed putting the station at Earth-Moon L5. People would live in the outer ring, connected to the central docking area by 6 giant spokes. The centripetal force from the rotation of the space station would give the inhabitants artificial gravity, allowing them to carry on regular lives as if they were under Earth's gravity. Because it's located out beyond the protection of the Earth's magnetosphere, the space station needs to protect the inhabitants from cosmic radiation. Back in the 1970s, the design team decided that an active magnetic shield would be too complicated and energy intensive. Instead, they proposed mining thousands of tons of rock from the surface of the moon and surrounding the outer shell of the habitats with protective bricks. If you want to prevent cosmic radiation, all you need is mass. A lot of mass. It would be too expensive to bring it up from Earth, but electromagnetic railguns on the moon could be constantly throwing material into space that could be added to the station. Giant mirrors would reflect sunlight into the station at an angle that prevents cosmic rays from coming in. Variations on the O'Neill cylinder were proposed over the next few years, like the Stanford torus and the McKendree cylinder, but they all suffered from the problem that they're inherently unstable. If you have a long tube rotating in space, it has two axes of rotation. Whichever is the longer axis is the preferred direction of rotation, which means you have to fight against your space station wanting to tumble end over end. O'Neill and the other solutions was to build their stations in pairs, which rotate in opposite directions from each other, balancing out the forces. Why don't we have one yet? Well, the amount of raw materials that will need to go into a space station of this size will help you understand why we've never built one yet. The larger version of the O'Neill cylinder would require 4.5 billion tons of rock steel, machinery, shielding, and other components. Even if the SpaceX Starship could bring launch costs down to $100 a kilogram, that would still cost about $450 trillion. It would require about 45,000 Starship launches to build one in low Earth orbit, not to mention getting it up to L5. And that's why it's so important for us to develop space-based mining and manufacturing before we have any chance of living in our rotating space stations. Although this sounds like science fiction, Blue Origin CEO Jeff Bezos laid out his long-term strategy for the rocket company at a recent conference. He supported the construction of space-based habitats, which look very similar to O'Neill cylinders. Someday, he hopes, the solar system could support 1 trillion people living and working out in space itself. And then, the vast majority of humanity will live at the Lagrange Points. I hope you enjoyed this tour through the solar system's Lagrange Points. We've already taken advantage of them with our missions and space telescopes, and I'm sure this is only the beginning. I can't wait to see what happens next.
Which shows you the tides of Earth. And you see the Earth here, and you're standing where the star is as the Earth rotates, and this shows you 1 month as the Moon goes around the Earth, and here's the Sun up at the top there. Now the influence of the Moon on the tide is shown by the grey elliptical shape. The pull of the Sun, its influence is shown by the whitey yellowy shape, and the overall combination of the two is shown by a blue ellipse, and you can't see the blue here yet because it's hidden just by the ellipse of the lunar tide. It will tell you whether it's a so-called neap tide or a spring tide. So neap tides occur when the Moon's here, and the spring tides occur when they're on either side of us. And you'll notice here that it will say whether it's low tide or high tide. So where it is here at the moment it's low tide, but if it moves into this bulge, that's high tide. And to explain why you get a bulge on the opposite side, they try to show it on this diagram of forces on the right hand side, and effectively it's because you've got centripetal force involved of the fact that we're not standing still, we are actually in a rotating frame of reference, and so consequently you get a bulge on both sides of the Earth from that. So if you watch for the next 2 minutes. So you actually see you get the highest of high tides when the moon and the sun are in line with each other. So that blue ellipse is much larger. And you get the lowest high tides and the lowest low tides when it's at right angles from the direction of the sun. Right, thank you very much, and we'll see you all next time.